Bom, bom dia. Muito obrigado por estar aqui com a gente. Obrigado também ao pessoal que está nos assistindo no YouTube. Hoje vamos então começar com o que é chamado o primeiro workshop de cristalografia de São Carlos. Esperamos que isso seja o começo de uma série periódica de eventos para juntar a comunidade cristalográfica de São Carlos mais uma vez e tratando de ampliar essa comunidade, as colaborações entre elas e conseguir dar treinamento não somente para nossos pesquisadores, sino também para nossos alunos, de tal maneira de motivar, formar recursos humanos e ampliar o escopo da nossa comunidade. Realmente a gente acredita, todo aquele que tenha assistido às palestras ontem, que a nossa cidade tem uma vocação para a questão de cristalografia, tem sido o centro da cristalografia de Brasil e da América Latina durante mais de 50 anos. Então, cabe a nós agora ampliar e, como chama? Aprofundar essa formação de recursos humanos, tratando de estabelecer novas colaborações e novos horizontes, né? Então, a ideia de hoje é fazer um workshop teórico prático, onde iremos apresentar os principais recursos dos novos equipamentos instalados no Laboratório Multiusuário de Cristalografia Estrutural, que inauguramos ontem, tratando de apresentar para vocês todos os recursos que esses novos equipamentos têm, qual é a possibilidade de cada um deles, que cada um deles oferece para a comunidade e como vocês podem colaborar e trabalhar conosco no uso e aplicação desses sistemas, né? Então, para isso, vamos ter uma série de palestras, começando agora. Vou tirar isso aqui porque fica meio complicado. Uma série de palestras, começando com a apresentação da IFSC. Depois então, primeiro vamos ter uma apresentação do presidente diretor da IFSC, o Daniel Oshima, que nos vai mostrar um pouco sobre essa colaboração que temos estabelecido por os últimos 35 anos aqui e que temos renovado agora com a instalação desses novos equipamentos e esses novos laboratórios. Posteriormente, teremos uma pequena mudança. Teremos a Selma falando sobre o Smart Lab Studio, né, que é um sistema muito interessante de processamento de dados de pó, que realmente torna a análise de dados de pó muito mais ameno, muito mais amigável e que permite obter muitos mais dados de uma forma muito mais rápida. Depois disso, teremos o Pierre falando sobre o uso do Smart Lab, do Synergy S, daquele equipamento que a gente montou lá, para difração de pó. Embora ele seja um equipamento de monocristal, desenhado para ser monocristal, as características dele permitem analisar também quantidades bem pequenas de pó, e vamos ver que essas qualidades fazem dele um equipamento muito interessante quando você tem pouca quantidade, você quer estudar a difração de materiais que não são normais ou que têm problemas, orientação preferencial, coisa por estilo, ou que se decompõem, ou que precisa variar em temperatura, ou coisa por estilo. Depois, isso será o primeiro do almoço, depois teremos o Pierre novamente, depois do coffee break, teremos o Pierre novamente falando sobre a aplicação do Synergy S em pequenas moléculas, e depois, hopefully, teremos o Luciano nos apresentando as coisas dele sobre os novos desenvolvimentos da Rigaku em materiais de cristalografia, tanto de difração de raio-x quanto de monocristal. Depois do almoço, que vamos ter é uma divisão aí. Vamos ter o Pierre falando sobre a aplicação do Cristallis, que é o programa de processamento de dados, principalmente aplicados a pequenas moléculas, e depois, contínuo disso, a aplicação desses mesmos sistemas para proteínas, né, que são sistemas bem separados. Durante esse intervalo, a pessoa que trabalha com pó já pode ir pegando suas amostras e falando com cadê o Pedro? O Pedro que está por aí, para que ele ajude vocês para fazer essas coisas. Aquelas pessoas que têm dados ou que precisam coletar dados de monocristal, falem com o João, que está aí, certo? Depois do almoço, então, depois das palestras do Pierre, temos o coffee break, e aqui do lado, e teremos uma sessão prática, tanto de monocristal quanto de, como é, de pó, certo? Onde o Pierre mostrará coletas de dados, como realizar coletas de dados de pequenas moléculas e de proteínas, né? Vamos soltar dados de coletas de dados de vocês, e a ideia é processar eles na sexta de manhã, né? Então, a sexta de manhã, de 8, na primeira parte da manhã, teremos o processamento dos dados que foram coletados durante a noite, de monocristal, e depois do coffee break teremos manipulação dos dados e processamento de dados e análise de dados de pó, né? Depois do almoço, isso vai ser sexta de manhã. Depois do almoço, vamos ter uma série de palestras de pesquisadores que vão falar sobre diferentes áreas, né? Então, a princípio, eu vou começar falando um pouco sobre fármacos analisados através de difração de raio-x de monocristal. Depois vem a Selma falando da aplicação de difração de pó, a análise de insumos farmacêuticos. Depois teremos o professor João Renato, do Laboratório de Proteínas, falando da aplicação do Synergy S ao estudo de proteínas, coleta de dados que foi feita ontem por Pierre. E depois teremos o Marcelo falando sobre minerais, né? Posteriormente, depois do coffee break, teremos o João Renato falando sobre o uso do Crystallography Mini, que é aquele difratômetro pequeno, a organometálicos. Ele trabalhou durante 3 anos trabalhando nesse equipamento aí, coletou dados espetaculares e publicamos muitas estruturas com esse equipamento aí, realmente fantástico. E depois teremos o Edgar falando sobre polímeros conjugados, e depois o professor Dorigueto da Unifal nos falará sobre as pesquisas realizadas em seu laboratório. E por último, para encerrar, teremos a palestra do professor Juan Carlos desde Rio de Janeiro, que nos irá falar sobre a aplicação de dados de difração de raio-x a quantum crystallography, né? A chart density analysis, né? E aí teremos o encerramento. Sim? Então, sem mais, vamos a proceder então agora à palestra do Danilo Shima. Danilo Shima é diretor-presidente da IRIX aqui no Brasil. Da IRIX é o representante oficial de Arrigaco aqui na América Latina. Obrigado.
Obrigado, professor. Então, bom dia a todos. Em primeiro lugar, agradecer a organização do workshop, o pessoal que está transmitindo, a plateia, o pessoal que também está assistindo isso através da transmissão no YouTube. Falar um pouquinho da Dairix, das linhas que nós trabalhamos, e um pouco do nosso trabalho, né? Então, a Dairix ela já está no mercado desde 1988. Começamos aí com a linha da Rigaco, como representantes exclusivos do Brasil, né? E desde então aí fomos, ao longo dos anos, aí, adquirindo novas representações, diversificando nossa carteira aí, de instrumentação. Vou falar um pouco de cada linha, rapidamente, né? E depois vou falar um pouco da parte de difração. Não vou aprofundar porque eu tenho os especialistas aqui, tem o Luciano, que é o nosso gerente da América Latina, tem o Pierre, que é especialista da parte de monocristal e proteínas, né? Eu vou falar um pouco mais breve das linhas que nós trabalhamos. Então, nós temos, na Rigaco, nós temos uma linha de fluorescente raio-x, de dispersão de comprimento de onda e energia dispersiva, né? Que a gente pode ver alguns equipamentos que são fabricados nos Estados Unidos pela Applied Rigaco Technologies, né? São equipamentos EDX-RF, que fazem análise de sódio até urânio, né, de bancada, para análise rápida. Fabricados aí no Japão, nós temos a linha de WDX-RF, né, dispersão por comprimento de onda. São equipamentos que nós temos de bancada, de chão, e equipamentos para a indústria, de alta produtividade, né. São fabricados na fábrica de Osaka, no Japão, né. Atualmente, nós temos uma nova linha aí de tomógrafos para materiais, né, em algumas aplicações também em vivo, né. Então, nós temos aí tomógrafos que conseguem varrer materiais em escala nanométrica, alguns deles também em bancada. Além da linha da Rigaco de raio-x, nós também trabalhamos com os raio-x portáteis da Thermo, né, que são os handhelds, né, as pistolas, para análise rápida. Então, é um equipamento mais voltado para a indústria. Você tira da caixa e já está analisando, ele te traz os resultados porque ele já vem pré-calibrado, né? Então, essa parte elementar seria essa que nós trabalhamos. E para você, muitas vezes, trabalhar com esse tipo de equipamento, você precisa fazer preparação de amostras. Nós temos máquinas de fusão, moinhos, prensas, né, da Equilab, que é uma marca espanhola, né. Aí também nessa parte de parte térmica nós trabalhamos com a Setembro, que é uma empresa francesa que trabalha com calorímetros, microcalorímetros, analisadores térmicos TGA, DSC, de alta sensibilidade, alta temperatura, né. Nós também temos alguns equipamentos para sistemas de adsorção para alta pressão. Da Setembro, que é uma empresa canadense, nós temos o sistema Trident, que é um sistema para análise de condutividade térmica. Na área ambiental, nós trabalhamos com análise de mercúrio. A Nippon Instruments Corporation, ela é uma empresa filha da Rigaco, né, fica baseada em Osaka, no Japão também. Nós temos uma área que a gente trabalha com pesquisas minerais, né? Então, além dos fluorescentes de raio-x, que nós trabalhamos bastante na indústria mineral, nós também trabalhamos com sistemas de medição de magnetita, detectores de metais para esteiras também. Da empresa AGL britânica, nós trabalhamos com reatores, sistemas reacionais, né, customizáveis, para você realizar scale-up, ou então fazer diversas simulações de reações químicas em paralelo, né. Então, essas são algumas das linhas que nós trabalhamos. E, além de nós trabalharmos com essa venda consultiva, tentando encontrar uma solução para as suas necessidades, nós também trabalhamos com a parte de instalação, manutenção, a gente também faz os treinamentos, né, e demonstrações. Então, dentro dessa gama aí, nós realizamos a parte de demonstrações, workshop, a gente vai até o cliente, realiza a demonstração, ou workshops, assim como estamos promovendo aqui, né. Mas nós também atuamos bastante na parte da academia, apoiando e participando de eventos, diversos eventos aí da área acadêmica, né, alguns dos eventos que nós trabalhamos, e nas feiras também de instrumentação, né? Então, era uma coisa que estava parada durante a pandemia, e nós estamos muito felizes aí de poder estar retornando e conseguir fazer alguma coisa presencial, né? E mostrando também algumas vezes que a gente vai até as minerações também e faz análise, faz os workshops dentro da empresa, né? Vou mostrar aqui também alguns dos nossos clientes, né? Teria que ter mais de um slide aí, mas eu estou mostrando alguns dos principais. Vocês estão aqui, da USP, né? Alguns de vocês também estão representados aqui. Peço desculpa aí se eu não representei todos que estiverem aqui ou estiverem assistindo, né? Então, desde 1988, nós já temos aí mais de 700 instalações pelo país, né? E como hoje o foco é cristalografia, eu vou dar uma pincelada aí sobre a parte de difração de raio-x, né, da linha Rigaku, né? A Rigaku do Japão produz equipamentos aí para pós-materiais, para fazer análise in situ, né? Nós temos equipamentos aí de bancada, né, de chão, e equipamentos de alta performance também, e alguns outros especializados. Um dos nossos carros-chefes aí na academia é o Miniflex, né, que é um difratômetro de bancada com 600 watts de potência, né, e atualmente nós temos uma versão que tem um chiller interno, então você não precisa, basicamente você só precisa plugar o equipamento na tomada e já pode realizar as suas medições. Então esse equipamento ele já está na 6ª geração, né, sendo que o primeiro foi lançado em 1973. Né? Então é um equipamento aí que ao longo dos anos e através do feedback dos clientes foi sendo aprimorado ao longo do tempo e incorporando novas tecnologias, né? Então já somam aí 50 anos quase, né, de tecnologia sendo aprimorada aí ao longo do tempo, né? E nós temos diferentes tipos de detectores, tem detector de cintilação, mas nós também temos os detectores rápidos, né, que são o detetor linear, e atualmente aí nós temos também a possibilidade de utilizar detetor 2D, né, um detetor bidimensional, né, para você realizar alguns tipos de aplicação com maior velocidade, né. Nós temos aí também alguns tipos de porta-amostras, né, porta-amostras com spinner, trocador de amostras, né? Então você consegue aí deixar todas as amostras preparadas e deixa a noite rodando, e no dia seguinte você está com o serviço pronto, né? Esse equipamento também permite fazer análise in situ, né? Então nós temos aí câmara de temperatura para até 500 graus, né? Isso é interessante aí para o pessoal que trabalha com farma, por exemplo, né? Pode fazer análise em função da temperatura. Para aqueles que precisam expandir um pouco as análises, né, as capacidades analíticas, nós temos equipamentos de chão, né, um equipamento que é bastante focado aqui para o nosso mercado, é o Smart Lab SE, né, que é uma evolução do Ultima 4, que vocês conhecem, alguns de vocês conhecem, né, e a grande vantagem desse tipo de equipamento é que ele é um equipamento automatizado. Antigamente você tinha essa necessidade de ficar alinhando o equipamento e desde o Ultima 4 os equipamentos são alinhados automaticamente pelo software. Uma outra coisa que veio a melhorar a linha foi um software intuitivo, que é o Smart Lab Studio, né, e que tem a função Guidance. Então, aquele usuário que está iniciando nos estudos, ele consegue configurar, com a ajuda do software, corretamente o equipamento para aquela determinada aplicação. Você seta a aplicação e o equipamento vai te propondo quais acessórios você tem que montar, né? E aí você vai colocando, vai compondo a ótica dele até acertar a configuração para rodar. E se você cometer um erro, ele vai te apontar, porque todos os acessórios eles têm sensores, então ele dá o feedback para você, né? Então isso é interessante aí, porque acaba deixando as pessoas mais autônomas em função de não conhecer aí aprofundamente a parte de configuração do equipamento, né? Mas para aqueles que trabalham aqueles que são experts também, você consegue acessar uma função que você consegue manipular parâmetros e recursos que normalmente o pessoal que entende bastante costuma se interessar. Então, é um equipamento aí que também possibilita você trabalhar aí com diversos tipos de análise in situ, né? Então, nós temos câmara de temperatura, câmara criogênica, câmara reatora. Uma coisa que nós temos aí exclusivamente através da Rigaco é o DSC simultâneo com o XRD. E além desses equipamentos, nós temos equipamentos especializados também, por exemplo, com equipamento para tensão residual, né? Equipamento para estresse, tensão residual, que são utilizados na indústria aí, ou em departamentos especializados, né? E agora também na parte de difração de raio-x, eu vou só dar uma falada, só uma pincelada, como eu falei, sobre os equipamentos de proteína monocristal, né? Porque o Pierre aí vai falar com mais propriedade, né? Então, nós temos equipamentos aí de grande porte, né? De médio, pequeno porte, né? E nós temos equipamentos aí que são dedicados para pequenas moléculas e outros para proteínas e pequenas moléculas, né? Nós temos equipamentos baseados aí em anodo rotatório, né? Para quem precisa de maior fluxo de fótons aí para aplicações que precisam que tenha esse maior fluxo. E nós temos também equipamentos baseados em tubo. Dentre eles, nós temos o Crystalography Mini, que a gente acredita que é uma grande arma para o pessoal que desenvolve, que faz síntese química, né? Que veio aí miniaturizar os equipamentos grandes e tornar mais acessível a técnica de cristalografia de pequenas moléculas, né? É um equipamento aí que possui detectores como os que você tem no síncroton, que são os detectores HPC, que fazem a contagem direta de fótons, né? É um equipamento de bancada, então você consegue trabalhar com ele em cima de uma mesa, não precisa de grandes instalações, né? Tem baixo custo de manutenção, e com os resultados que você acaba adquirindo com esse equipamento, você consegue realizar diversas publicações, né? É um equipamento que também possibilita a utilização de sistema de criogênico, né? E o mais legal agora é que ele está disponível aí no Instituto de Física da USP, né? E vocês que tiverem interesse em conhecer o equipamento e testar, o professor Javier aí irá nos ajudar aí com essa condução de demonstrar o equipamento para vocês, né? Um dos grandes trunfos da Rigaco, a Oxford Diffraction, com a união com a Oxford Diffraction, foi a utilização, foi a concepção do software Chrysalis Pro, que é um software bastante intuitivo e que mudou um pouco a questão de como você coleta e processa os dados. Tornou muito mais intuitivo a utilização, a parte de cristalografia de pequenas moléculas, né? E ele tem diversos aí plugins que você pode utilizar para facilitar suas medições, né? Então, é um equipamento, é um software bastante intuitivo, com interface gráfica, né? E é um software livre. Você pode baixar ele, uma vez que você se cadastra no fórum da Rigaco, você consegue baixar uma cópia do software e utilizar esse software para processar os seus dados. Então, você pode, inclusive, ter dados que você coletou no síncroton e utilizar o software para fazer o processamento desses dados. E, além desses equipamentos home lab que nós chamamos, nós também temos equipamentos de grande porte, né, baseados em anodo rotatório, que é um exemplo de um equipamento com fonte de anodo rotatório, e de um lado você tem a técnica de biosax, e do outro lado você pode fazer pequenas moléculas ou proteínas, né? E atualmente a Rigaku lançou um novo equipamento, que é o difração de elétrons, né? E é um equipamento aí que eu acredito que possa fazer bastante ruído aí na comunidade cristalográfica, porque ele consegue aí atingir escalas ainda menores na pesquisa que já vem em andamento, né? Então, gostaria de agradecer e eu vou pedir licença para vocês para mudar para o inglês, porque assim eu consigo incluir meu colega Pierre. So I would like to thank you everybody here for helping us to make this workshop to happen. I'd like to thank FAPESP, who helped us, the institute and us to make the purchase of the Synergy S here in the Physics Institute. I'd like to thank also Direct Crew. Without them, I was not able to be here and make this happen. I would like to thank Mr. Oshima. He's my father here, and he helped us building the history of Rigaku in Brazil. My mother as well. So they taught me that also important than reaching your objectives is the way to get there. So it's the relationship with people like the Physics Institute from São Carlos show us that more important for me than reaching these objectives is to have very good people with us. Very good, very, very good, because they are also the pioneers here. And it's a very long time relationship with them. So we have Augusto here with a very old instrument that was still working since the refurbish of the laboratory. I don't have a picture of Geraldo Catarino, but I have a new picture of him. This is to show a little bit about how the instrument came, and everybody was very anxious to open the boxes and to assemble the instrument in the lab. So everybody was working together to make this happen. So there's people from the lab, the students, Julio Hernandez, Manuel, Paulo. And also after the installation, we had Pierre coming here to tune in the instrument and to give application training. And it was an extensive week of trainings, and it's going to be very helpful, this workshop, to teach you participants on this technique. So I like to thank also Rigaku Corporation in Japan, our colleagues from Rigaku Poland. This instrument is made in Poland, Synergy S, but with parts of different parts of different countries. Our colleagues from Rigaku America. And we also have, here I finally found a picture of Geraldo Catarino together in the table with us yesterday. So, and Rigaku was very nice to support a happy hour with us, for us today. So for those who are here in the event, we are going to make a happy hour from 7 p.m. Então, a gente vai fazer um happy hour aqui, a Rigaku está dando esse suporte para a gente. Vai ser na Choperia Calil, no bar Choperia Calil, é um restaurante árabe, né? E ele fica na rua Carlos Botelho, na Avenida Carlos Botelho, né? Número 1737. Fica muito próximo daqui, então dá para a gente ir andando. Um dos motivos também que a gente escolheu ele. Nós teremos o salão fechado para nós, né? E, enfim, vamos poder aí confraternizar, dançar e vamos ter música ao vivo também, né? E uma coisa que eu percebi essa manhã é que o cantor, ele é o Thiago Branco, mas ele parece muito o Wolverine. E aí eu acabei me dando conta que nós teremos Wolverine cantando e o professor Javier no mesmo bar. Então, é isso, gente. Espero vocês lá. Agradeço aí. E bom workshop para todo mundo.
Bom, espero que todos tenham gostado da surpresa, né? Temos hoje, vamos ter hoje então um happy hour depois do trabalho, assim que realmente agradecemos novamente a Dairix e a Rigaku por essa oportunidade de poder estar hoje. Assim que juntem-se comigo em mais um aplauso para agradecer esse. Realmente a Dairix tem sido um parceiro muito grande em toda essa empreitada, né? E, como a gente fala, isso não foi uma compra de um equipamento, foi mais uma parceria, né? Porque junto com o equipamento a gente comprou a manutenção dele por 6 anos, a ideia de manter o equipo funcionando por um longo tempo, como todos sabem, aqui, como chama? No hemisfério sul é uma coisa complicada. Uma coisa é você ter um equipamento, outra coisa é manter ele funcionando de forma adequada por um tempo longo. E a gente tinha que garantir isso, tinha que garantir não somente que o equipamento ia estar lá, sino que esse equipamento ia estar disponível por um longo tempo para um monte de pessoas, né? Então, isso foi a ideia dessa parceria com a Dairix, e isso tem ajudado muito durante todos esses anos. A gente agradece imensamente essa parceria, que como eles falaram, como vocês viram na foto, isso começou há 35 anos, então não é uma coisa de agora, né? Até recentemente aquele equipamento estava funcionando, aquele ano rotatório, acho que foi o último ano rotatório desse tipo a ser como se chama, colocado fora de funcionamento no mundo todo, né? Então, era realmente até difícil conseguir peças, né? Então, mas realmente uns equipamentos muito robustos, e isso foi uma das coisas que a gente sempre como se chama, valorizou na Rigaku e a parceria da Dairix. Bom, hoje vamos ter, como se chama, a possibilidade de mandar fotos, assim que se vocês têm fotos antigas e tudo mais, me mandem, porque a gente vai colocar hoje, na apresentação, vamos ter a possibilidade de colocar fotos aí no happy hour, e isso vai dar um bom conjunto de discussões e lembranças e um bom tempo aí. Então, agora vamos ter a apresentação da doutora Selma Gutierrez Antônio. Ela fez o doutorado aqui na Unesp em Araraquara e atualmente ela é consultora da NOC Consultoria na área de difração de raio-x, principalmente método de Poe, trabalhando também com a Dairix. Ela nos vai explicar parte daquele programa, aquele conjunto de programas que o Danilo falou, que é o Smart Lab, que não somente consegue gerenciar o equipamento, que não é o nosso caso, mas também processar os dados de uma forma muito adequada. Então, essa eu vou mostrar algumas das maravilhas que esses programas fazem e que temos à disposição para nós agora. Então, Selma, por favor.
Bom dia a todos. Queria agradecer a organização do workshop, que convidou a gente para estar aqui. Agradecer a Dairix, que com a parceria que a gente tem, também permitiu que eu esteja aqui para dar essa apresentação sobre o programa do Smart Lab. Essa apresentação é de um programa, então o mais fácil seria mesmo a demonstração do programa, mas como a gente vai ter o hands-on mais tarde, então a gente pode pegar todas as dúvidas que vocês tiverem e mostrar mesmo na prática como a gente pode utilizar esse programa para resolver os nossos problemas, principalmente pelo método do pó, que é o que a gente tem mais ferramentas dentro do Smart Lab. Bom, como o Sinerg é a cereja do bolo de vocês no momento, né? Que também, né, consegue fazer a medida, além do monocristal, também tem a possibilidade de fazer a medida pelo método de pó também. E com ele, o programa mesmo vai conseguir transformar os dados do Sinerg num padrão de difração, aonde a gente vai conseguir trabalhar lá no Smart Lab com todas as ferramentas que a gente tem. E é um programa que no Sinerg você consegue transformar em várias os dados, né, de vários formatos, que você pode trabalhar também no GSAS, por exemplo, mas o principal aqui é que a gente consegue transformar no formato ASCII, que lê direto lá no nosso Smart Lab. Há uma informação importante, né, mesmo o Sinerg fazendo essa medida, a gente tem que sempre tomar cuidado com a qualidade do padrão de difração, né? Às vezes as pessoas confundem intensidade com resolução, mas pelo método do pó a gente sempre precisa se preocupar melhor com a resolução dos picos do que ter um padrão de difração, uma intensidade gigantesca. Então, nunca confundir um bom padrão de difração de raio-x para a gente fazer todos os cálculos que a gente pode fazer e tirar todas as informações das propriedades físicas do material. Então, é importante a resolução do padrão, não a intensidade. E o programa também, do Sinerg, a gente tem a possibilidade, então, de vocês estarem brincando lá até você conseguir um padrão de difração com uma resolução ótima para a gente estar fazendo as análises. O Smart Lab, ele tem essa carinha. Ele, na verdade, ele é pensado para qualquer pessoa assim, eu quero fazer só quantificação. Então, ele tem lá a gavetinha de quantificação. Eu quero só fazer tamanho de cristalito. Então, é só a gavetinha do tamanho de cristalito. Então, se você se acostuma com o formato, né, do programa, você vai facilmente navegar entre as caixinhas, que ficam aqui do lado direito. Então, primeiramente, você escolhe qual é o objetivo que você quer, né? E depois você vai trabalhando nas abinhas até você ter o seu resultado. Uma das particularidades do programa, que eu acho bem interessante, como a gente consegue fazer os gráficos facilmente, né? Principalmente esse gráfico inicial, que a gente só quer mostrar que a gente conseguiu o padrão de difração, que a gente conseguiu a nossa fase. Então, facilmente a gente consegue distribuir uma gama de padrões das suas medidas e faz o gráfico para o seu trabalho. E também, facilmente, a gente consegue fazer os difratogramas em 3D, que fica também bem legal. Principalmente quando a gente tem lá a câmera de temperatura, que o Danilo falou, que você tem diversas medidas. É bem interessante fazer esse tipo de gráfico, que a gente consegue ver, principalmente, as transformações de fases. Por exemplo, nos polimorfos dos fármacos, que a gente consegue ver facilmente, então, uma estrutura se desfazendo e a outra aparecendo. É bem interessante e é muito fácil a utilização do programa e a formação desses difratogramas, desses gráficos. Aqui não ficou legal, né? Mas uma outra opção que tem aqui no Smart Lab é da gente fazer... ele verifica para a gente as similaridades dos difratogramas. Então, eu consigo, se eu tenho 200 difratogramas lá de minerais, vai ter alguns mais semelhantes, outros não. A gente pode fazer a análise do cluster e o programa mesmo já vai fazer lá nossa separação ali, a gente já vai saber quais os lotes que são de uma porção de fases e de outras. Então, são pequenas facilitações do programa que ajudam bastante no nosso dia a dia. Bom, tudo no padrão de difração, né, vai começar com a identificação das fases, que é a parte principal para a gente ter uma boa análise do padrão de difração de raio-x. Uma outra ferramenta que auxilia bastante aqui no Smart Lab é que ele coloca, por exemplo, a lista de picos lá para a gente. A hora que a gente dá um load lá dos nossos dados, ou que você pode... Ele abre diversos formatos, né? Lógico, todos os formatos da Rigaco, mas também abre o formato XY, que você consegue obter de qualquer outro equipamento. E lá ele vai, então, se você tem se você coloca os dados dos medidas da Rigaco mesmo, vem todas as informações importantes sobre a medida, mas, se não, vem as informações básicas, que é do esteto e intensidade, mas que já auxilia na nossa identificação. Então, ele coloca lá a lista de picos, e eu tenho como, inicialmente, né, se eu já sei qual que é o meu material, eu simplesmente posso selecionar os picos que eu sei, que eu tenho 3 fases, e eu sei que o pico 1, 2 e 3 é da fase 1, e 3, 4, 5 é da outra fase. Muito fácil, eu consigo, então, designar esses picos, e já faço a identificação desses picos aqui na tabela, e já tenho uma tabela prontinha, onde eu posso, então, mostrar, né, baixar essa tabela. Aqui eu só dei um print da tela, mas eu consigo exportar para abrir no Excel e ter, então, os picos aqui e com a identificação das fases. Que também depois sai no reporte que o programa faz, que fica bem completinho, você não precisa fazer mais nada, porque o reporte vai ter todos os seus resultados. Voltando aqui. Então, o importante aqui é que, além de você estar identificando as fases, os picos aqui, essa identificação bem inicial, né, sem nenhum conhecimento muito específico, você também você pode, então, colocar se esse material é cristalino ou amorfo. Para o programa vai ser importante, porque se você tem interesse de saber o quanto é cristalino o seu material, vai ser nesse momento aqui que o programa vai saber o que você designou como amorfo ou não. Mas é interessante porque nem todos os trabalhos têm tantas informações assim, né? Isso para a indústria farmacêutica, por exemplo, ou para quem trabalha na indústria, que já sabe quais os picos das fases e precisa desse relatório rápido, essa é uma forma bem rápida e coerente de você estar mostrando o seu resultado. Na indústria farmacêutica, por exemplo, a gente tem polimorfos que a gente só tem as informações de 3 ou 4, 5 picos mais importantes daquele polimorfo. Então, é a única informação que eu tenho. Então, a única forma de estar identificando aquele material é selecionando, vendo, né, se você tem os picos que está descrito na patente. Se você tem, você coloca aqui, descreve ele como um pico cristalino e coloca o nome dele lá, porque você identificou com as informações daquela patente. Sempre, né, a gente sabe, sempre a gente tem que ter as informações para validar o que a gente está fazendo. Então, depois que eu tenho lá o meu padrão de difração, e a identificação é a mais importante, como eu já falei, né, porque o programa, o Smart Lab, como qualquer outro, ele vai dar o resultado segundo o que a pessoa está colocando ali. Então, se está certo ou se está errado, é você que tem que dar o conceito para ele. Não adianta você colocar polimorfos errados e o número vai dar, mas a coerência é você que tem que ter. Então, essa primeira parte de identificação é importante por causa disso, para você não levar a erro lá no final e falar que você tem laranja em vez de maçã. Mas isso é a coerência do pesquisador que está fazendo a análise. Mas a facilidade aqui do Smart Lab na identificação de fases é bem interessante. Então, tem um programa de search já incluído lá. Eu não falei assim também, né? Mas o Smart Lab foi feito para aquele outro difratrômetro, né? O Smart Lab. Então, ali a gente já faz tudo. Ele tem a aba da medida, se vocês tiverem já colocado ele, se você tiver esse equipamento, você já faz a medida, já troca de aba, já faz a identificação, já troca de aba, já faz a quantificação e já faz tudo num programa só. Então, na parte da identificação aqui, você fez lá a medida, passou para a parte aqui de identificação, a gente tem a opção de fazer uma busca nos bancos de dados, que é o gargalo, né? Porque a gente tem que ter um banco de dados para comparar ali o meu padrão com o que tem no banco de dados para eu confirmar a minha identificação. O interessante aqui do Smart Lab é que ele também trabalha com o CODE, que é um banco de dados livre. Então, a gente tem a opção de trabalhar com esse programa, mesmo se você não pagou lá para o PDF 4, PDF 2, para ter o programa, né, para ter o banco de dados, que é realmente muito caro, você tem a opção do CODE. E o CODE, hoje em dia, né, tem muitos dados. Principalmente para quem trabalha com materiais inorgânicos, ele praticamente resolve tudo, né? Mas tem alguns orgânicos, orgânico metálico, e ajuda bastante no processo inicial aqui da identificação. Então, a gente tem lá, a gente pode selecionar os átomos ali, né, que a gente tem. E, se por um acaso você tem uma medida de fluorescência do equipamento da Rigaco, você também já pode direto baixar aqui e ele já faz a escolha aqui dos átomos que vão ter no seu material e já tem o trabalho completinho. Então, tudo trabalha em conjunto. Mas, como quem trabalha na pesquisa, na verdade, deveria saber o que é o material, né? Não precisava assim, ficar tão procurando tudo. Então, você tem a opção, se você tem, como a gente está aqui na universidade, a gente tem o acesso ao BDC, ao banco de dados lá do BDC, e a gente tem acesso a SSD, e você tem lá também todos no SSD a gente tem todas as estruturas cristalinas inorgânicas, e também tem o Cambridge, que é as estruturas orgânicas e orgânico-metálicas, que estão determinadas, né? Lógico. Então, se você tem, né, se a gente está aqui na universidade, se você é pesquisador, você tem lá já o seu próprio banco de dados que você pensa que sabe ali que deu o seu material. Então, se você já sabe, ao invés de fazer o search match, de ficar lá procurando ficha por ficha qual que bate com o seu material, você pode achar aqui direto o CIF, né, que é o da estrutura cristalina, e faz também a sua identificação. Toda essa parte a gente vai ver melhor lá direto no programa, né, que é mais fácil, porque aqui a gente só vai mostrar as potencialidades do Smart Lab e ver na real quando a gente estiver mexendo no programa. Um benefício aqui do Smart Lab que eu achei maravilhoso é que também você, quando trabalhando principalmente com minerais, tem muitas fases, você consegue identificar a primeira, a segunda, a terceira, aí tem lá uma meia dúzia de pico com baixa intensidade, que eu fiz o search match, não deu certo. Mas o que eu faço? Eu venho aqui nas configurações do search match e escolho somente os picos que estão faltando para fazer essa identificação. Assim, eu consigo muito mais fácil estar terminando a minha identificação, né? Primeiro, a gente identifica os picos mais intensos, que é o mais fácil, o programa já acha logo, mas esses picos de baixa intensidade realmente sempre são um problema, e esse benefício aqui no Search Match ajuda bastante. Okay. Bom, depois que você tem certeza que fez o seu trabalho direitinho, identificou suas fases direitinho, a parte mais interessante, quando a gente tem a difração do pó, é que a gente consegue fazer essa quantificação de fases na medida, né, e facilmente, né, nos últimos anos, como além dos equipamentos, os softwares também têm atualizado muito, e a gente tem muitas opções aqui para estar trabalhando, para a gente fazer uma boa quantificação de fases. Então, tem o método de Hitwell, né, que a gente utiliza aqui para fazer a quantificação, e se você identificou seus materiais certinhos aqui, você já pode fazer o refinamento, e no final do refinamento você ganha de brinde a quantidade de fases que você tem. Também você consegue estudar o tamanho de cristalito e a microdeformação do material, se você tem uma boa medida. E, como eu disse, a Rigaku pensa sempre em resolver o seu problema rapidamente. Então, ele põe tudo em gavetinhas. A gente, aqui no método de Hitwell, está acostumado a trabalhar com já as equações e já saber onde que acha ali os resultados de microdeformação e tamanho de cristalito. Mas, como a Rigaku quer ainda te auxiliar, ela coloca uma gavetinha a mais ali, depois, que não é nessa parte do refinamento, onde que ele vai avaliar apenas o tamanho de cristalito e a microdeformação. Se você não quer saber o quanto você tem de nada, você vai direto na outra gavetinha e consegue analisar, então, o tamanho de cristalito e microdeformação. Aqui, mais mesmo, é para fazer a análise para identificação e quantificação. O programa, geralmente, ele já ajuda você, porque ele já faz a hora que você identificar, ele já vai fazer um fit inicial, né, que ele coloca lá com valores iniciais de uma equação pseudo-void, com as informações da estrutura cristalina, né, para ajustar as intensidades e a posição dos picos, um ajuste inicial. Com esse ajuste inicial, o programa já verifica quais os parâmetros que vão ser refinados ali para a nossa quantificação. E ele mesmo já coloca aqui, por exemplo, aqui nesse exemplo, inicialmente eu não cliquei em nada, só coloquei na aba de refinamento, e ele já colocou vários parâmetros para serem refinados. Então, o programa mesmo já analisa, já fala, você pode refinar isso, isso e aquilo. Sempre, né? ele vai estar inicialmente refinando. Se você colocar para não refinar nada, ele já vai estar inicialmente refinando o background e o shift, que é o deslocamento o deslocamento dos picos em relação à preparação da amostra. Mas aqui a gente tem o fator de escala, os parâmetros de rede, o perfil, né, que é a equação que você utiliza. Tem a textura, que aqui ele coloca a textura, que seria a orientação preferencial, e a estrutura cristalina aqui, que também tem a opção, se você se você precisa, né, saber algumas outras informações da estrutura, precisa refinar alguma posição de átomo, refinar os parâmetros térmicos, a gente refina aqui, nessa caixinha da estrutura. Mas é bem interessante, por exemplo, quando a gente está fazendo análise de minerais, que às vezes tem bastante orientação preferencial, o próprio programa já vem aqui e coloca que está para refinar a orientação preferencial. Mais ainda, porque a orientação preferencial, na maioria dos programas, tem duas formas de serem corrigidas, né? O método de March-Dolase e o método dos esféricos harmônicos. No caso do March-Dolase, a gente precisa saber qual a família de planos que está orientado. E o interessante é que o Smart Lab já coloca para a gente lá. Eu não preciso ir lá no difratograma, olhar e ver qual é o HKL, ou ir lá na literatura e saber qual que é a família de planos que está orientado. O próprio programa já vai colocar aqui para a gente, facilita bastante também. E também, o que é interessante, que você pode, numa fase, corrigir a orientação por March-Dolase, na outra pelos esféricos harmônicos. Você não precisa escolher só um método para corrigir a orientação preferencial, que é bem legal também. Então, aqui você consegue... É lógico que ele tenta te ajudar colocando tudo ali num quadradinho só, mas você consegue abrir para editar os parâmetros e consegue ver tudo ali que está refinando. Não é uma caixa preta que você não sabe o que você está fazendo. Você consegue, então, abrir os parâmetros e ver o que você está refinando. E aqui você tem, então, os parâmetros de rede, o perfil, a orientação preferencial, tudo aquilo que eu falei está aqui, e aqui você pode mudar e alterar. Na questão do perfil, a pseudo-void que ele utiliza é bem interessante. Inicialmente, você considera o material isotrópico, mas facilmente você consegue trocar para anisotrópico ou trocar de função. E também, né, para quem está querendo analisar tamanho de cristalito e microdeformação, a gente também tem como trocar facilmente pelos parâmetros fundamentais. E se você utilizou lá os dados da Rigaco, não precisa se preocupar em nada, porque você já está lá com todas as informações do equipamento já colocado lá na parte dos parâmetros fundamentais. Então, já está tudo lá, o raio do goniômetro, a fenda solar que você utilizou, todas as fendas que você precisa saber para usar os parâmetros fundamentais. E também você pode aqui entrar uma outra janelinha de parâmetros, e você pode, que é onde você vai trocar aqui a função de perfil, ou, se por um acaso, o background, você quer também, tem outras 3 opções de ajuste do background, além do default do programa. E também tem mais 2 equações que corrigem esse deslocamento shift, né, que é devido à preparação da amostra. E, como resultado, a gente tem lá o finalzinho lá, que a gente, no final, você fez um bom refinamento, tem os índices de qualidades adequados, você consegue, então, o final ali, tem um resuminho bonitinho da nossa análise quantitativa, ou com gráfico, ou só com a tabelinha de quantificação. Bom, você fez lá trabalhou no seu material, mas depois você fez mais umas 5, 6 sínteses e queria partir daquele refinamento para fazer os outros refinamentos. Facilmente aqui, quando você está em Ritable, você só coloca aqui em Multiple Data, você consegue, então, download de mais diversas, quantas medidas você quiser, e a partir desse seu primeiro refinamento, ele vai refinar os seus outros lotes com nenhum problema, e você já vai ter o resultado de todos os outros. Então, né? Daí o próximo resumo seria o resumo de vários, a partir desse primeiro. Então, você trabalha direitinho lá no seu primeiro, se você tem vários semelhantes, facilmente você consegue fazer essa análise de diversos lotes, né? Bom, o maior problema do método do PO é a identificação. E a identificação, depois você identifica e você descobre que aquela sua identificação está certa. Mas ninguém fez um monocristal para a gente, ninguém determinou a estrutura para a gente. Como que a gente quer? Mas a gente precisa codificar, principalmente no pessoal da indústria, né, que não tem tempo de ficar fazendo pesquisa que nem a gente. Eles precisam identificar. Então, enquanto ninguém, né, faz um monocristal bonitinho para determinar a estrutura, a gente tem que trabalhar, a gente tem que saber quanto tem na nossa amostra, na nossa mistura. Por isso, e pelo desenvolvimento, né, tanto dos equipamentos como dos softwares, se teve essa preocupação desde de 2000 com métodos que a gente consiga quantificar sem a estrutura cristalina, ou com a estrutura, ou com pelo menos o material indexado, né? Se a gente pelo menos tem que saber a célula unitária. Então, em 2006, acho que apareceu o primeiro método que pensava já nessa parte, né, de fazer a quantificação, mas em 2006, né, teve o primeiro método. Mas nesse método eu tinha a minha mistura, mas eu precisava ter o que eu não tinha estrutura cristalina determinada, eu precisava ter ele separado, bem identificado, para fazer análise com padrão. Então, um procedimento bem minucioso, né, para a gente fazer a quantificação com o método, para não precisar de ter estrutura cristalina. Mas em 2016, 2018, eu esqueci de colocar a referência aqui, mas o Toraya publicou esse método, que chama de método, que é uma derivação, que ele consegue, então, pegar as informações. Você tem que saber a fórmula química do seu material, pelo menos, e você consegue facilmente, então, colocar a composição aqui no programa e conseguir fazer essa quantificação sem estrutura cristalina. É bem interessante, é bem confiável e é bem interessante. Por exemplo, eu tenho um comprimido e quero fazer uma engenharia reversa. Se eu sei os componentes daquele material, eu ponho as informações, né? Eu posso colocar uma lista de picos, se eu sei que a fase desconhecida tem aquela lista de picos que eu vou saber, ou você pode colocar mesmo uma medida de difração, né? Você faz a medida, por exemplo, tem um comprimido de um IFA e uma celulose microcristalina, que é um recipiente muito utilizado. Você pega, faz a medida da celulose microcristalina, só adiciona ali, e você consegue, então, fazer a quantificação. Você precisa, então, basicamente, a fórmula química. Você pode colocar, se você sabe, só as informações de célula unitária e grupo espacial, ou você pode colocar só as medidas, ou você pode colocar os picos, a lista de picos, ou você ainda, lá naquela primeira parte que eu mostrei para vocês, onde você identifica os picos, naquela identificação dos picos também, ele vai utilizar aqui. Então, ele vai utilizar aqueles picos que eu selecionei como sendo daquela fase. E, no fim, então, eu consigo essa quantificação da mesma forma. Eu acho que, de todos os benefícios do Smart Lab, esse realmente é o mais interessante, principalmente com essa questão de você conseguir pôr uma medida aqui para fazer num comprimido, por exemplo, eu não vou conseguir quantificar além das fases cristalinas, eu consigo também quantificar diferentes amorfos no meu material. É lógico, com um bom trabalho, com uma boa medida, sabendo fazer direitinho, né? Não adianta, o método do pó não é só lá e apertar um monte de botão de fazer ele rodar. Você tem que ver a coerência física e química que você está obtendo. Mas é bem interessante e você consegue fazer muitas coisas com esse DD método que só tem aqui no Smart Lab. Uma outra caixinha, uma outra gavetinha que a gente tem lá, que eu já falei, né, a parte do tamanho de cristalito e microdeformação da rede, que você só apenas põe lá você só apenas põe o seu difratograma, identifica as fases e logo passa aqui para a parte de análise de tamanho de cristalito e microdeformação e logo vocês conseguem todos os gráficos que você tem, a verbar e tudo mais. Uma outra caixinha, se você não quer nem saber muito o que tem no seu material, só quer saber a cristalinidade. Lá no começo, quando eu mostrei, eu falei assim, eu vou identificar um pico com um pico amorfo. Então, eu colocaria aqui esse pico como o pico amorfo do meu material. Eu simplesmente, aqui, né, na verdade, eu busco ele primeiro, né, eu só clicar aqui nesse botão no software, ele já vai achar um halo, né, que justifique ali o seu amorfo, e você só clica cristalinidade e ele já vai te dar o resultado sem nenhum problema. Mas, assim, também a gente tem uma outra gavetinha que a gente só quer fazer a nossa curva de calibração, a gente quer saber o limite de quantificação do meu material ali. Então, você tem como fazer essas análises de curva de calibração, tanto com padrão interno como padrão externo. Então, facilmente você dá load lá de todos, uma gama de misturas que você fez, que você tem certeza, para a gente estar ali fazendo a curva de calibração. Não existe um número mágico de quanto é o menor número, a menor porcentagem que um padrão de difração do método PO vai quantificar. Isso tem que levar em consideração vários fatores, como o próprio material, se ele difrata mais ou difrata menos, em qual é a mistura dele. Se o material está misturado numa quantidade muito grande de material amorfo, o limite de detecção, com certeza, vai ser menor do que se ele tiver todo cristalino, numa mistura toda cristalina. Mas, aqui nessa parte de quantificação de curva de calibração, fica bem simples. Você só faz o load dos dados, coloca as informações das fases, e ele mesmo lá já faz a sua curva e tem lá os seus resultados. Basicamente, é isso. Na verdade, né, você também... esses são o mais dia a dia que você pode fazer ali com o seu Smart Lab, que é o que você faz pelo método do pó. Mas também tem outras gavetinhas bem interessantes, que por exemplo, fazer o PDF, né, que é uma técnica nova que está utilizando aí, e já tem, então, uma parte para estar trabalhando com PDF, né, que seria uma outra gavetinha. E também, se você não conseguiu obter lá o seu monocristal, como deveria ser, tem a opção de a gente fazer indexação com o método do pó. E o Smart Lab também, a gente consegue fazer essa indexação de estar determinando as dimensões da célula unitária e um grupo espacial. Depois, a gente precisa de alguns programas, o Expo, né, para fazer a determinação final do material. Mas eu queria agradecer. E alguém tem alguma pergunta? Não. Mas, então, tudo isso a gente vai ver depois, então, lá no Run the Zone. E vocês podem me procurar e eu demonstro para vocês qualquer uma dessas características do programa que vocês gostariam de saber.
Muitíssimo obrigado, Selma. Realmente muito interessante. possibilidades que podemos fazer com isso daí. Vocês viram que dá para fazer desde identificação até quantificação, análise, realmente muito completo. Aí vamos ter a possibilidade de fazer medidas hoje à tarde, então quem tiver dados ou quem tiver compostos para medir, pode contactar o Pedro, que está por aí escondido. Aqui está, o Pedro é ele, estava escondido mesmo. E então para fazer as medidas, aí o Manuel vai fazer as coletas de dados para você e já com a SEMA já podem quantificar seus dados e resolver suas estruturas. Então, ficamos agora para o coffee break, vamos dar uma parada de meia hora e depois a gente continua aí, assim a gente continua mais ou menos com o cronograma do YouTube, né, para que o pessoal não se perca aí. Então, voltamos aí para depois, daqui a meia hora. 10h30 a gente está de volta. Muitíssimo obrigado, senhores, e até daqui a pouco.
1, 2. Oh.
Oi, oi. Coordenador chamando as pessoas. Por favor, votem para o anfiteatro. Tá difícil. Competir com o café e o pão de queijo tá difícil. Sorry, Pierre. Coffee and pão de queijo is a strong competition for you. Sometimes I think that the students come to the workshop just for the coffee breaks and the sweet. Yeah. Okay, let's start for the second part of our presentations of this morning. In the second part, we will switch to English because we will have a couple of presentations from Pierre Lemararest. Try to speak in French. That is not my my strong point. He will speak to us first of all about how to use the smart lab to measure powder diffractions that they have some quality, some strong point that can do some things that you cannot do in the ultra, in the Ultima 4, in the Ultima 4, that this is the normal powder diffractometers. And after that, he will speak with us again about, let me remember what was the second talk. About how to use the smart, the synergy as to new developments and single crystals. And so this will be the two presentations of today. The presentation of Luciano will has been moved for the first part after lunch. So that's saying, let me welcome to Pierre. Pierre studied physical chemistry, makes a PhD in physical chemistry and small molecule crystallography in University of Rennes, in France. Y está en Rigaku since 2004. He is the application scientist of Rigaku Americas, and he is very welcome here. Please, Pierre. It's working?
Let's see. Can you all hear me? Yeah, good. All right. Yeah. All right. Thank you. Thank you, everybody. Good morning to those that I haven't seen yet. I would like to say that I've been here actually since the past Friday. Being the application scientist for Rigaku, I was here so since Friday to train Professor Elenas and his group on their new shiny little toy. So I thought I would start by also thanking you guys, Javier and the students, for the warm welcome, all the sweets in the lab every day, and the nice barbecue also on Saturday. So lots of food. I think next week when I come back to Houston, I have to diet a little. No good that way. And run. So I thought I would start by actually, run a little summary about what we're going to do. Let's hope that this thing works. This thing needs to be turned on also. There you go. Yes or no? There. So as since I was here already for training, so Professor Elena asked me to stay longer and take part into this workshop so that I can explain to everybody, you guys here, as well as those who are listening to us online, all what can be done now with this new system. Okay, so there's going to be a lot of information thrown at you guys in English. I'm sorry, I'm a little self-conscious. I'm the only one presenting in English and not in Portuguese, but so pardon me for that. By the way, if you have any question, go ahead and raise your hand. It's cool, right? So it's better that we have a conversation. So yes, after all my presentations here, hopefully you will know all what can be done now with the Synergy S, which couldn't be done before on the smaller X-ray system, the Crystallab Mini. So how it can be used to do the research here at USP, but as well as all of you who are used to sending crystals to Professor Elena, what kind of analysis you can ask him to do now. Okay? So we will, over my few presentations, so we will talk first about how to collect powder. Although the new toy downstairs in the other building is a single crystal diffractometer, you can also collect powder on it. Then my second session this morning, just before we break for lunch, is going to be about single crystal crystallography in general. And I will touch upon what I could define as standard crystallography. I'll talk also a little bit about variable temperature experiments, as well as high pressure crystallography. Okay? This afternoon, I think after lunch, Luciano is first going to give a presentation, and then I'm going to take over again to demonstrate to you our program and how it handles difficult data sets from single crystal, including twins, including a superstructure, and when the crystal is playing with you like it's moving during data collection, for instance. And then my last session this afternoon will also be about protein crystallography. Okay? And after that, with whatever time remains, we will go to the lab, and then I'll run a demonstration of the system. Again, depending on how much time remains, but I'll start with probably one of my standard side-eating crystals, the reference crystals I travel with. And then, so we'll go on with collecting on local crystals. Javier just told me that someone is down there in front of the system already collecting crystals for some of you who have brought crystals. So we are cooking here. All right, so now indeed, so I'm an application scientist at Rigaku. So I've done my PhD in France at the University of Rennes. And it was I actually come from chemistry and small molecule crystallography. So then I got accepted to do a postdoc in Houston, in Texas, which was the first time I crossed the Atlantic Ocean. Okay, and I did my first postdoc in 4 years at the University of Houston, and then I decided I wanted to learn protein crystallography. So I switched department at the University of Houston, moved from chemistry to biology, and then learned how to do protein crystallography. Okay? Here from 2000 to 2004. Then I joined Rigaku, but it was to fill a position in Europe. So there I am, crossing the Atlantic Ocean again, this time in the other direction. And I was the Rigaku crystallographer in Europe for 2 years, actually, and we were based close to London in England. And then after 2 years near London, then I decided to come back to Houston, and there I am crossing the ocean, the Atlantic Ocean for the third time, okay? To become a protein crystallographer at Rigaku Americas, so back in Houston. And then since 2018, I think it's 2018, my boss at Rigaku asked me to come back to small molecule crystallography. And that's why I'm here with you today. So from Houston, we cover, in terms of sales, of course, but also in terms of application support, we cover North America, South America, Australia, New Zealand. So as you can tell, I'm having a very tough life. I'm traveling all over the US. I'm here with you this week. And in this past May, like 3 or 4 months ago, I was in Sydney, Australia. Okay? So like I said, I have a tough life. Just in parenthesis, since I see there are quite a few young people among us today, like Mr. Oshima, for instance. So I want just a little parenthesis. Whenever you guys will be ready to look for a job, think about companies like Rigaku, what we call vendors. Okay? Companies like Rigaku, like Derek's, we always look the Could be our salespeople, but especially our scientist people. We look for people like yourself coming out of a PhD or postdoc or a master's in science, okay? So keep that in mind. It doesn't have to be about X-rays. It could be infrared, NMR, whatever you learn to do during your master's, PhD or postdoc. Keep in mind that you can join vendors companies like Rigaku, and then you do what I do. If you think that might be a life that you enjoy, then think about it. So just a little piece of information thrown at you. I'm saying that because when I got that job at Rigaku, I had never thought of that kind of job before. It came to me. I didn't really apply for it, and then I took it, and I never looked back. Okay, so as you can tell, I'm having a blast. Okay, so that was for my quick presentation about myself. So now I'm going to switch to, this thing is maybe not. All right, a little information or brief history about Rigaku. So we are on the single crystal side. Rigaku is actually Rigaku Oxford Diffraction. And that's because in May 2015, the two companies actually merged. Okay? The reason for that is that so Rigaku was mostly prominent with very high flux expressors that are called rotating anodes. And therefore, most of our customer base was in proteins, okay? All over the world, but mostly proteins. We admittedly didn't have enough to offer in terms of small molecule. On the other hand, Oxford Diffraction, based in Oxford in England, were mostly prominent in small molecule. And they had wonderful small molecule systems. By the way, they are the company who invented the dual source seal tube system, which was copied after by everybody else, right? But they are the ones who invented it in the 90s. So basically, it was just a very good marriage between these two parts. Nobody was fired because everybody has their own expertise, and so basically it was a really good merging. Okay, so out of this marriage, then. Different products came out of that. Of course, we improved. We came up with new components, mostly. So the there. So the microfocus. We came up with new microfocus seal tube expressors. We came up with which was so the optics for that are manufactured in the US. A new type of detector technology. I mean, we are not the ones who invented that technology, but nevertheless, we came up with our own after a little while. That's these are manufactured in Japan. And then faster goniometer as well as the program coming from Oxford Diffraction. Okay? So then we some of our existing systems here were upgraded by some of these new parts here, in particular the Crystallab Mini, which is one of the two systems that Professor Elena has down in his lab. And then, of course, we came up with a new series of systems, and we call that the synergy systems. Synergy after name, so to speak, after the merging between the two companies, because the big brains from both companies sat together and tried to design new, better instruments. So this is the Synergy S, or the Synergy series, and the new toy that was just installed here at the Institute of Física de São Carlos is the Synergy S. Okay, so that's why these two are in orange, because that's what is present in Professor Elena's lab. So among these new systems, so the Synergy I and S are microfocus seal tube, while the R and W here are rotating anode. So again, rotating anode, much stronger source. There's a ratio of between 1 to 10 in terms of strength of the beam, right? Of course, if you have more money, you have to have more money to buy the rotating anode. Now, I want to point to you here that you see the word here, microfocus, is highlighted. And that's the big point about this new technology, this new diffractometer. They are microfocus X-ray beam. And it starts with the electron beam that you generate to shoot on the target to generate your X-ray photons. This is the electron beam that is micro-focused. By that, I mean that we apply a magnetic force onto the electron beam to make it small, 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 small. So now we hit the target, copper, molybdenum, or whatever you have, at a very, very tiny, tiny point, okay? And then because all the photons come out of a tiny point, then with the mirrors, we can come closer, and then we can keep those photons tight, 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 tight to come up also with a smaller and more intense X-ray beam. So small beam, much more intense. So that means that now you can collect on much smaller crystals and much faster. It's a completely change of way of working. It's a change of paradigm, okay? So now, as a result, we get stories from our existing customers. People telling me, you know, Pierre, I've been using the Synergy S for 3 or 4 years. I still can't believe how fast it goes, right? Others tell us, I don't have a life anymore. Because at the end of the day, I have collected a few more data sets and structures solved, but then the crystallographer has to finish up the structures and write the reports. They have no life anymore, right? So they slow things down. The other thing is that, sorry, but when you tell students that now the machine is so good, students start having a weird behavior. So there's even less effort made in crystallizing proper crystals. So there's something that dried out in a beaker. Now there's something apparently solid at the bottom of the beaker. They go to the crystallographer. Can you analyze that? Can you get me the structure? Okay. So anything that is not liquid or gases, can you analyze that for me? Can you get me the structure? Okay. I've got someone telling me about a couple of his students who would start a data collection and stay in front of the computer, staring at the screen, because they knew that the structure would come out very quickly. So the setup that is down there in Professor Alina's lab, so the program can collect data, process data, and solve the structure at the same time. Once you know that oftentimes the structure comes out after a few minutes, even as just a partial data set has been collected only, then some people, they stay there and they stare at the screen until the structure comes out. Okay? So this is going to be a completely change of way that you appreciate crystallography and work with an X-ray instrument in the lab. It's very exciting, okay? But now you have to work harder as a chemist to produce more crystals. The other thing is that in terms of small crystals, the limiting step is no longer going to be the strength of the beam, it's going to be your hands and your eyes, because you can go so small with crystals that at some point you can't see the crystals anymore under the microscope, but the X-ray beam will. Okay, so I went down to 10 microns or so, and then that's really, really hard to see crystals on your little loop if the crystal is only 10 microns in size. So keep in mind that now it's a completely different game compared to what was there before. And by the way, this is not only Rigaku, right? This is the new technology, right? It's not only Rigaku, to be honest. Okay. All right, so now that I've done all these introduction, so let me dive a little bit more into my really first presentation about powder data collection with the Synergy S. So this is how the Synergy S looks like. It comes within its own enclosure, which is completely X-ray safe, which means that when this thing is closed, you can walk around as much as you want. You're never going to be irradiated with X-rays. Okay? It seems obvious, but this is still very, very important to tell. And the diffractometer itself is that thing here behind the front door, and it's shown in a bigger format here on the right-hand side. So the source is on the left, then you have the goniometer here on which you mount the sample, and then you have the detector here on the right, and that's what I'm going to talk about now in a little bit more details. So I'll start with the source, and so again, I'm going to try not to throw too much details at you, but I still need to mention a few things so that you understand what this thing is all about. All right, so this, like I said, this is a micro-focus seal tube. Remember that this is the electron beam that hits the metal target that is micro-focused, and from there comes an X-ray beam, which itself stays smaller and stronger. Now, the electron beam is so focused when hitting the metal anode that you have a high density of electron. Therefore, you don't need to actually generate a strong beam of electron. You have a small beam, high density of electron, okay? So basically, the source has a power of just 50 watts. Okay? All right, yeah, 50 watts here. 50 kilovolts and 1 milliamp. 50 watts. I repeat, 50 watts. This is nothing but a light bulb in your house. Nothing more than that. And yet the system, the beam is probably 10 times stronger than whatever existed before. Okay? So that's why I insisted before that this is a complete change of technology. It's not like a linear progress. This is like a leap forward in terms of X-ray diffractometers for the home lab. Okay. All right. So now the other thing is that you can have the choice of 1 or 2 wavelengths among three choices. So you can choose 1 or 2 among copper, molybdenum, and silver. You choose whatever you want, doesn't matter to us. You can choose 1 now and add a second one later. You can choose 2 now and make the switch after, doesn't matter. So people use one or the other according to the wavelength, obviously, and according to the type of analysis they want to do. All right, so now the goniometer. So the important thing here is that the goniometer is a full 4 circle. So meaning that the goniometer has 4 axes that move around. Okay, and I'm going to explain to you as to why this is important. And then the detector. So a new detector technology as well. It's now a photon counting detector, and you should remember these words. I will get back to them in a few minutes. But the new detector technology now counts photons. All right. So now a little bit more details. So in terms of some specifications about the beams, the X-ray beams that we can manufacture now. You see the beam coming out of this system, the full width at half medium is 100 microns, okay? Which means that you have a big beam, but 50% of the beam already comes from a tiny hole of 0.1 millimeter. And that's because you have a beam with a Gaussian shape, just like this. Okay, so this is now the size and shape of the beam, Gaussian. Whereas the beam that is used on the smaller X-ray diffractometer in Professor Elena's lab, the Crystal Lab Mini, that beam is much larger and has a flat intensity throughout. So larger and flatter and lower. Whereas now you have a Gaussian-shaped beam, smaller and with a peak, like with a mountain in the middle, right? So that's why the beam is now also so strong. To get back to powder, now that you have such a small beam, the main point of, or the main advantage of that system to analyze powder is that now you can use very small amount of samples. So you no longer have, to have a certain amount of sample to spread onto a sample holder like you do on the smart lab. Okay, so very small amount of sample. That you can put in thin capillaries, very thin capillaries, or in single crystal loops. The same loops that you use for single crystals. Now, instead of mounting a crystal on it, you pile up powder inside it. So because less amount of sample is needed. Okay. That's next. So here are a few examples of capillaries, whether be they glass capillary or Kapton capillaries. So here is a few examples of a mount. What I like to do also is put a little bit of clay onto the magnetic basis of a regular mount for single crystal. Put a little bit of clay and you plant a little capillary in there. All right. So capillaries, it's probably not too surprising to you, but the main point here is that okay, you can use thin capillaries. Okay. Now, something that some of you probably have never seen is this. You actually use this kind of single crystal or crystal loops to mount powder now. So typically, you want to wet out the loop with oil. So usually I actually get rid of the oil inside the loop. And once the fiber, the edge of the loop is wet with oil, then you dip it into a little bit of powder sample under the microscope. And you end up with this. Sometimes this thing works, sometimes it doesn't. Okay, now it doesn't. So you end up with that, okay? So that little circle here has a diameter of 100 microns. So across here, in that orientation, you have 0.2 millimeter by 0.2 millimeter. And on the side view, you see here that the thickness of that sample was only 100 microns as well. So very, very small amount of powder that you can work with because the size of the beam on the Synergy S is so small. Okay? So that's the first advantage, small amount of powder sample. All right, so now we've seen we talked about the beam, we talked about the sample preparation. A little bit of quick comment about the hardware versatility here in terms of the fact that if you have a dual wavelength source like we have in the other building, so there's one source here at the front and one source at the back. And so it's easy to switch from one to the other without touching the sample. If you want to make an analysis with copper and then with moly, then no problem. You don't even have to switch you don't have to actually touch the sample. You don't have to switch anything on the hardware. It's computer controlled. Within 3 to 4 minutes, you have switched to the second wavelength. All right, now the next thing I want to mention is the goniometer. And I think Professor Elena mentioned something about it in his little introduction. So the goniometer is, how to say, completely computer-controlled detector distance and suitable for what is called the Gandolfi type of strategies. Okay? And all right, so let me come back. The reason why it is or what we call Gandolfi data collections is, or type of data collection, is whenever you can collect by orienting your sample in different ways in the beam. And you do that whenever your sample adopts preferential orientations in the mount. Your grains are all aligned from the same way, and so you don't have a proper randomization of your powder data. So what you want to do then is force those grains to adopt different orientations in the beam, and therefore you tilt your capillary or your loop to different angles in the beam, and you do that via that geometry here, that kappa axis. You see how the whole mount here, or that axis with the mount at the tip, is tilted. So you can have that straight up or also at different angles. Right? And you collect a scan of data in different sample orientations, and then you merge everything together, and now you have a really, really nice data randomization data set. Yeah. All right. So this is briefly the data collection interface that allows you to do that. Here, so in this example, I chose 4 settings, or 4 different kappa angles. So first of all, I implemented the Gandolfi feature and implemented 4 settings for kappa. So the set of scans looked like that. So this is the kappa. So each line is one scan, so a different crystal orientation. So there you see here that on the first 4 scans, the four first lines, the detector position is the same. So really the detector remained at the same position, but then for each scan, the kappa angle is different. Okay, so 4 scans were collected with the detector there. The detector would move to collect another 4 scans, and so on and so forth. So the kappa angle here is shown here, and this is the angle between the red arrow here, which is phi, and the vertical arrow, which is omega, the blue arrow there. Okay, and so these 2 angles, the red and the axis, the red and the blue axis, are reported here in the data collection strategy as well. And I'm showing this to you because in addition to collecting data in different crystal orientations, once you have kappa non-zero, then you see the red axis and the blue axis are no longer collinear. And then you can also rotate at the same time along both axes to get, again, better data randomization. So between the different angles, and at each angle, the rotation of both 2 axes at the same time, the grains of your powder now adopt a whole lot of different orientations in the beam, and you get a nice smooth rings of powder. Okay? Here is an example. On the left side, this is just phi rotation. So I kept my sample straight up, rotated along phi. And you see how uneven the distribution of intensity is along those rings, so that comes from preferred orientations from the powder grains. On the right-hand side, here, so you see I already moved kappa to a non-zero angle, and I rotated the same time along phi and along omega, okay? And right away you see that the distribution of intensity is already better. See that part of the ring here versus that part. And that was one scan. So if you do that, on the whatever is on the right-hand side here, you do that at several kappa angles, then you have a beautiful, smooth powder rings and beautiful randomization of your powder data. So this is the second important thing that you can do on the Synology S in terms of powder data collection. All right, what is next? And the next thing to come up here in this presentation is the fact that you can also control the beam divergence. All right, so what is that? So here is a schematic on the right-hand side. The source is on the left. It goes through your sample here, and then there is your detector. Obviously, you need to focus your X-ray beam onto a little point here, which is the sample. And so as a result, you need to make your X-ray photons converge pretty quickly onto the sample position. Whatever converge will diverge after that. And the divergence, the larger the divergence, the larger the reflections from your crystal, and the larger the powder rings as well. And then the larger these features, then you have overlaps, and your data are not always so good. Okay? So we have a way to control the divergence of the beam here, and so you see the smaller beam inside here in red that yields that or generates that smaller red reflections as well. So what we do is that so there's what we call a beam divergence slit, okay, and that will sharpen the peaks so that you have better peaks separation, and all that is computer controlled. And here is an example that usually wows people. So this is an example, obviously, on a single crystal, and I'll show an example on powder right away after. So here, this is a crystal of a protein called catalase. You see the huge unicell parameter, 230 angstroms, and obviously, when you bring your detector too close, all the reflections here are on top of each other because the reflections are too large, and so they are too large and too close, so they are on top of each other. Really, they are not separated. By closing that little slit and decreasing the beam divergence, so I managed to decrease the size of these reflections, and that's what happened. I closed a little bit, closed, closed. So when here I went from completely data that I could not use at all to nice rows of reflections where the reflections are nicely separated, okay? And there I could solve my protein structure without problem. This is all computer control, like I said, so all you do is that you pick up that little bar here and you slide it slowly from right to left until you see the picture or the resolution of your reflections as you wish. An example of powder is this. Lanthanum hexaborate with the full beam. You see that at first, so I have fairly large fuzzy rings. Maybe here on the left-hand side, which is a very high resolution, maybe there's a double ring there, maybe, okay? By decreasing the divergence of the beam, I got this. Double rings everywhere, okay? So I made, each one of these rings was indeed made of two small rings. I managed to make the width of these rings so thin that now I could separate them also, although they were so close to each other. So that little separation of rings here comes from the alpha 1, alpha 2 little difference of wavelength, which is really, really minimum. By making I could make the ring so thin that now I could separate them. Okay. So if you could do that for your powder data, then your full width at half maximum for your peaks is much better. Your spectrum, your plot of intensity versus 2 theta shows really, really sharp peaks. And of course, if you have a longer unit cell dimension, then you can resolve your peaks much better also. On the plot of intensity versus I of a sigma, this is the full beam, and you see that only at very high resolution did I start seeing some peak splitting, but now by closing that little slit and decreasing the beam divergence. Now I've got also these peaks here. All these that are now start getting separated. So again, before, before, after. Okay. So keep that in mind because those our users who do powder on the Synergy S, they almost always use that little slit to get the sharper and sharper peaks. All right, so I will pass on the detector really, just to not to go over time. I'm just gonna make a summary of the things that you should remember about that new detector technology. So there is no electronic noise. That's because that detector, like I said before, is now counting photons. You're probably used to CCDs, for instance. CCDs are photon integrating devices. Meanwhile, which means that during an exposure, let's say you expose your sample for 15 seconds. So during 15 seconds, you can't do anything but wait for all the photons to accumulate on the detector per pixel. Then you have to close the shutter, and then all those data need to be read out. Okay? So that's why it's a charge integrating. The technology needed to do that generates a lot of electronic noise. So that's why when you use a CCD, you need to first collect a dark current image. And this is a calibration of the electronic noise from your detector. You don't need to do that here. This technology allows to catch a photon, count it, and discard it right away. So we count each photon individually. Okay? And the technology that we can use to do that get rid of whatever is creating electronic noise on CCDs. So then that has two advantages. You have your overall background on your images that will be lower, and you have no limit in the exposure time that you use. And the electronic noise coming from CCD increases in a linear fashion. And so there's nothing you can do about it. At some point, it will keep growing and growing and overwhelm your data. That's why on CCDs, you have limits on exposure times. You don't on this detector technology. So whenever you have a weakly scattering powder, then you shoot the hell out of it for 2 hours if you want to. You're never going to overwhelm your detector. Okay, so that's another advantage of running collecting powder data on the Synergy S. The other, so there is the sensitivity is higher. What we call the dynamic range is much higher. Also, the dynamic range is whenever you overwhelm your pixels, and then at some point they can't read more data. That's what happens when you turn your camera to the sun. Okay. So this detector technology, since it catches a photon, reads it, and throws it away right away, so you can, obviously you're much less likely to accumulate so many photons per pixel that a pixel will become overloaded. So it has really lots of advantages. And again, it really accompanies the leap forward that we just explained to you before in terms of X-ray sources. Now there's also a leap forward in terms of detector. And all that happens in ambient conditions. So CCDs, you have to cool them down. You usually have to have the electronics under vacuum, cooling, vacuum. So then you have to use a system of pumps and plumbing and stuff like that. And these things break. There's no need for such devices on this new detector technology. So it works in ambient conditions, much less chances for the detector to break. There is actually no maintenance. It works or it doesn't. All right, so that was for a brief thing about the detector. You see all these things I'm going to pass over and finish here the first part of that presentation. So just a slight summary. To remind you that so small beam, small intense beam, very flexible goniometer, so that you can get around preferential orientations of the powder grains in the beam, and very sensitive detector with no electronic noise. Okay. All right, so routine data collection in our program Crystallis Pro. So I'm going to pass over that, but you enter your name, detector distance. Your target resolution in theta, and this is up here on the right-hand side that you choose to run only one 5 scan or go for the Gandolfi options where you tilt your compound in different orientations in the beam. Here you can even ask Chrysalis Pro to add 2 theta detector positions to collect across your resolution range, so that between consecutive images at different detector position, you have more overlaps. Better overlaps means that all the data on different images will be better scaled to each other. And set up your exposure time, and off you go. Okay? So what Chrysalis Pro will do then, all the images that are being collected will be scaled and merged together. You don't have to do that. Chrysalis Pro does all that for you, and will come up with an intensity versus 2 theta plot right away. Okay? As soon as the first image is collected, actually, the first result from data reduction appears. That plot is then updated as soon as the second image comes out, and so on and so forth. And you sit and watch. Like I said, Chrysalis Pro will do the scaling and merging of all data to all images together. It will run a couple of corrections on the data, especially for those rings, those photons that hit the edges of the detector. So there's an oblique incidence, just like a drop of water that hits the floor. The drop it gets elongated. Same goes for X-ray reflections. You need to correct for that. Okay? So Chrysalis Pro does that for you. You don't have to even think about it. And it will output the resulting data in the format that you need afterwards to go to a powder dedicated program to do your fancy analysis. Okay. So Chrysalis Pro is our single crystal crystallography program. Therefore, it will run the measurements for you on powder. It's not going to do the indexing, right? Or any kind of analysis. Chrysalis Pro is a single crystal program, once more, doesn't know everything about all the fancy things that you can do with powder. So that's why you need to take the resulting file here and throw it into a powder dedicating program, which you have here at USP with Smart Lab Studio. Yeah. And then that's it. Okay, so and there is a typical file on the left-hand side output by Chrysalis Pro. The one thing that Chrysalis Pro will do is a qualitative analysis for phase identification. What you can do is enter the unit cell parameters that you expect. Okay? And then having the unit cell parameters, Chrysalis Pro can calculate back the location that your peaks should have, and these are the little ticks here at the bottom. So these ticks come from a set of unit cell parameters that I had entered manually into Chrysalis Pro. And so then you compare the location of the little ticks here with the location of your experimental spot peaks, and allowing you to do phase identification. So lots of our single crystal crystallographers do that actually quite routinely. So it's really, really good system to do a qualitative analysis. For quantitative analysis, that's when you have to take up the resulting, file, the file that puts together the intensities versus 2 theta, and you have to throw that into a powder dedicated program. Okay? So that third-party program, such as Smart Lab Studio, will do the Lorentz polarization if needed, the beam polarization if needed. If you need to do a background subtraction for such fancy analysis like PDF maybe or something like that, you can do all the measurements in Chrysalis Pro as well on your sample as well as your empty mount. You output the reflection file, so to speak, for each, and then you throw that into the powder dedicated program to do the background subtraction in that program. Okay. But remember, Chrysalis Pro will not do that, but will collect all the data for you and put everything into an intensity versus 2 theta file. So all kinds of subsequent analysis, the same indexing, phase quantification, read-veil refinements, you name it, again, in a third-party program. And here are some examples of third-party program, GSAS, PDXL, and then the Smart Lab Studio from Rigaku, which you guys have been using for a while. Okay, so there's not, in terms of Smart Lab Studio, those of you who know how to use that, again, collect your data on the Synergy S and throw the results into Smart Lab Studio, unless you want to do something qualitative real quick. Okay? And I think I'm going to stop here for the powder part of, for this first presentation about powder. So remember, with the Synergy S, you can use very, very small amount of samples of powder. The beam is so small and strong that we will get data for most of your powder sample. You can do something fancy like Gandolfi type of data collections to get around the problem of preferential orientations of your grains in the in the beam, and use the detector technology to expose for a long time if you need to get the data that you need. Yeah. And once you got your data, you can throw everything to Smart Lab Studio, and at that point, you're a better expert than I am in Smart Lab Studio. End of powder. Okay? Questions, comments? Anything?
Any question? You wanted to ask something?
Thank you, Pierre,
Yep.
for a presentation. And I have a question about background subtraction. I noticed that in the diffractogram you showed in the first part, in small angles, you have a little background.
Always.
Always you have this. And I noticed that in one of our samples that we measured, we have this too. And for us who study minerals, it's interesting to always calculate the amount of amorphous phase we have.
Right.
And for this, we need to calculate the background correctly. And my question is how to quantify the percentage of this background is due to the equipment, and after this to subtract for me to calculate the right quantity of amorphous phase.
That's becoming too fancy for me in terms of powder analysis. Okay, so again, there's the you're talking about the part of the amorphous the amorphous contribution from your sample to the overall data, right? And you're saying that you're seeing that even after you have corrected for the background, right? You still have a little bit of a bump. That's what you're saying? Yeah, right, yeah, okay. No, so then you'll have to talk to a powder specialist for that, right? Maybe, I don't know, maybe Selma can help me out here. But I don't know, I've never done such fancy analysis of powder samples. So to quantify the amount of amorphous data coming from a given sample.
Maybe.
Você quer saber a codificação de amorfo? Certo. Então, a gente pode fazer isso, porque realmente, nesse caso específico, você tem que ter realmente esse cuidado. E fica fácil fazer isso naquela parte lá do DD método que eu mostrei para vocês. Porque daí você consegue fazer um branco, né, e tirar, então, esse alargamento instrumental do que realmente é o amorfo do seu material. E é até interessante para depois você fazer com e sem a correção, para você mostrar realmente que a diferença, né, da quantificação. Mas facilmente a gente pode quantificar no DD método, por amorfo, porque se a gente usar a parte de quantificar a cristalinidade direto, ele vai avaliar tudo debaixo da linha do background e vai considerar tudo amorfo. Então, se você usar o DD método para utilizar a quantificação e tirar essa parte, né, da parte instrumental, você vai ter o amorfo realmente do seu material. Ou se você usar um padrão interno, você pode usar um padrão interno e você vai conseguir conseguir a quantificação correta e não precisa pensar na parte instrumental, porque daí você vai ter o padrão interno para estar de ponto inicial e vai saber quanto tem de amorfo no seu material. Então, duas formas, DD método com branco ou com padrão interno.
Obrigado, Selma. Sim, então, another question for Pierre? No? So, Pierre,
Next.
you would like next?
Next.
Okay.
you know how this thing is shut down? Keep pushing on it. Thank you. All right, next, we're now switching to single crystal. Single crystal from, so from powder, we're jumping now to single crystal. And this is here that I will talk about regular crystallography. What time is it? Okay, I think we are on time. And I will talk also about variable temperature crystallography as well as high pressure crystallography. Now some things are getting a bit fancy. So the last two parts on the variable temperature, actually that's okay, but especially high pressure. Now when you master high pressure, you're becoming a pretty good crystallographer, as well as a pretty good person at handling the diffractometer. Right, next, then let me start with a slide a bit similar to one of those that Danilo showed before. A quick product line overview, just to make you understand where the systems that are now, the two systems that are now in Javier's lab, where they stand in terms of the overall line of product, in terms of strength and this and that, okay? So in the middle, I've got samples, systems that can be used for both small molecule and protein, really. So, and it starts with the Synergy S, the microfocus seal tube, which is the one that I was talking about already before, to collect powder samples, okay? So then the next one down is the Synergy R, and now we're talking about rotating anode. This is there that I told you that for us, an approximate difference or ratio between in terms of beam strength is 1 to 810 here from the S to the R, rotating anode. So just for your quick information, a seal tube is fixed. So the beam of electron that hits the metal hits always the same point. And then if you hit it too much, then your copper, your moly, or your silver will melt down, okay? So therefore the tube has to be cooled down, of course, number one. But number two, you have to pace yourself in terms of the strength of the electron beam that hits the target. Okay? So as a result, that electron beam cannot go beyond a certain strength, and that's why the Synergy S runs at 50 watts. Now imagine that the target here, copper, moly, or silver, if you start moving it, so now the electron beam is not always hitting the exact same spot on the target. So now you can hit it with a stronger electron beam. That's the point of the rotating anode. It is rotating. And that's why we can shoot it with a stronger beam of electrons, and that's why the X-ray beam that results from it is also much stronger. All right, so next, so that Synergy R is one wavelength, but at Brigaku we also find a way to have this rotating anode with two different wavelengths, okay? And you switch between one or the other. We are the only company that master that technology of dual wavelength rotating anode. So in Professor Elena's lab, there's a dual wavelength seal tube, but there are actually two different sources and therefore two different beams. The rotating anode, this is one source. So that anode that rotates, we take this is actually the exact same anode here than there, but here we actually add a layer of a different metal on one side of the anode. Okay? And then there's a whole system that moves the anode one way or the other, so that one metal or the other is exposed to the electron beam. And then now, because your wavelength is different, you need different optics. So we have two sets of optics within the same chamber. The whole thing rotates when you change wavelength. It's pretty complicated, and yet for you as a user, you just do one click in Chrysalis Pro in the program, and you sit back. Within 3 or 4 minutes, you have changed wavelength. All that with a rotating anode that shoots a super beam of X-rays. So now people buy these systems here in the middle, for both, Synergy S or and DW, for both small molecule and protein. So now you can go one way or the other towards systems that are almost only used for small molecules, and others are almost only used for proteins. And of course, that has to see with the strength of their beam. For small molecule, you don't always use or need such a strong beam. So that's why here we have the Synergy I, which is basically the little brother of the Synergy S. Everything is almost the same. The beam is a bit weaker, the goniometer is a bit slower, and the detector is smaller. Okay, so as a result, you can collect the same data. It's just going to take you longer, okay, probably 4 or 5 times longer. Then we have the Benchtop system here, the Crystallab Mini, that has a weaker beam, only moly, and a smaller detector as well. Okay, so again, things are becoming smaller and smaller and less strong if you got less funding money from the funding agency. It's all about money, basically. So then on the right-hand side, for those people who, the fancy protein labs, like big pharmaceuticals, big protein labs in universities, they also buy rotating anodes. We have 2 types of rotating anodes for them, what is called the 007 HF here, which is really the same as the RDW, and then we have even bigger rotating anode. So I told you that the rotating anodes, they rotate, so the larger the radius of your rotating anode, the longer it takes for the same point to be irradiated again with the electron beam, so you can shoot it even with a stronger electron beam. So the rotating anode here for the so-called FRX is pretty big, right? And it's actually hard to carry. But now you get very, very, very strong X-ray beams. Okay, so you can destroy crystals all the time. Now the reason why, so now this is the Synergy Custom, but the point of the custom is now you can put 2 beams, 1 on each side. So you have almost 2 systems for the price of 1.5. Okay? And again, so you can actually collect data on both sides at the same time. When you open both shutters, there's no loss of beam intensity, and you can have 2 people collecting data at the exact same time. Some of our customers, they have a single crystal setup on one side, and they have a small angle scattering setup on the other side. So the protein people, they can also analyze the shape or the configuration of their proteins in solution, and then compare with what they get in the crystal form. So now you need a pretty big lab with a table that is about 3 meters on each side, and then so it's really, really fancy. Okay? We are going to install one like that soon in Sydney, Australia, so I'll get to go to Sydney again to do training over there. And the last thing I want to mention here on the right-hand side is, again, especially for these big protein labs or pharmaceuticals, we have also an automatic sample changer, a robot that will mount crystals for you, automatically center the crystals in the beam, and automatically collect data for you. All you have to do is prepare all all your crystals in a dewar. See at the bottom left here, you have a dewar filled with liquid nitrogen, and you have what is called little pucks in there, and you mount your crystals in there. And then you have nothing else to do. The robot is then going to pick up each crystal one after the other, mount it, center it, collect data, put it back in the liquid nitrogen, move to the next, and so on and so forth. So big pharmaceuticals, big protein labs, synchrotron beam lines they can use their own robot, but many of them use ours also. Okay, so you see now you have the whole panoply of systems, from a small benchtop system here for X-rays to this big system where you can have two persons working on at the same time, as well as using a robot. Okay, now and what we have here. In Sao Paulo is these 2. So the Crystallab Mini that has been there for several years, and that's how it started here in Professor Elena's lab, and then Professor Elena just upgraded with that guy. Okay, so these are the 2 that we have here in Sao Carlos. And so I mentioned those things already before. If I mention, I'm going to talk now more precisely about the Synergy S. This is a slide I used before, so the beam, the goniometer, and the detector. I'm not going to go through that again, but of course, whatever I said before pertains to my second presentation as well. I will talk a little bit more about the goniometer and the strategy program that goes with it. Okay, so having fast and precise goniometer, that's what allows you to collect good data and complete data on all crystals, even those that have the smallest geometry for their lattice. So remember that there are 4 axes, okay? So here is that little orange arrow there. This is called phi. It goes through the axis of the goniometer head, and then you have kappa. Okay? The kappa is the angle that tilts the sample in different orientations in the beam. So now, kappa has for us for that goniometer has a wide range of motion allowed, basically almost all over 360 degrees, and there. Now, number 3 is the blue arrow here. I'm colorblind, so I can't always see where I point my dot, so that's why I have to come here. So the blue arrow here, which is called omega, and that's always the data collection, axis. So basically phi here and kappa are used to orient the crystal in a certain way in the beam, and once it's there, then the system starts rotating slowly along omega, which is always the vertical axis, slowly, and then you collect 1 scan of data. Your second scan will be a completely different crystal orientation. Kappa will be different, phi will be different, and again, the system is going to start collecting or rotating the sample along the vertical axis, and that's going to be your second scan. And you need so many scans and so many images per scan to get a complete data set, and that's when you trust the strategy program. You know? So our omega axis here can rotate as much as 180 degrees at the same time. If you go beyond 180 degrees, so let's say that this edge here of the goniometer will start slamming into the detector. Obviously, you don't want that to happen. The detector itself, as shown with this curved arrow, can swing on both sides of the beam. And of course, you want the detector to go far to the side of the beam to collect your high resolution reflections as well. When the detector stays in front of the beam or go to a moderate so-called swing angle, then you collect your moderate or medium resolution data, maybe up to 1 angstrom or so. And especially for copper, when you need your data to about 0.8 angstrom of resolution, you need to move to the side more and more. So you need to have a completely flexible detector going on both sides of the beam as far as possible to be able to even collect complete data set and be able to publish. So that goniometer does all that for you. What you have to remember to keep in mind as a result is that detector will collect complete data set, even the lowest symmetry possible. Lattice P1, where there's basically not even a center of inversion. All the reflections coming out of the crystal are unique. You need to collect absolutely everything. You will get 100% completeness with that detector. With that goniometer and small detector, no problem. That's the thing for you to remember. Okay? Now the sphere of confusion, and this is, again, I'm throwing data at you because in the future, whenever you are building your own lab and buying your own diffractometer, these are the kinds of things that you need to be sure the system that you buy fulfill, right? So what is called the sphere of confusion is how much the center of rotation of the goniometer moves or changes whenever you move the goniometer. Ideally, you have your crystal there. However you move your goniometer, your crystal should not move, should stay there. Otherwise, your crystal moves out of the beam, and then your data, the intensity go down. It's this kind of mechanics basically is never, ever perfect, never perfect. But you try to have it as perfect as possible. And our own sphere of confusion is 10 microns. Okay. So really 0.01 millimeter, our goniometer, when it moves around and dances around, it should not move by more than 0.01 millimeter, which will ensure that your crystal stays in the beam. So remember the kind of beam that I told you that we have, that thin beam with a huge intensity in the middle. It would be a pity to generate that kind of beam and have your crystal move all over, around, in and out of the beam. The goniometer ensures that your crystal stays in the beam. So we have to think about all these things, right, when we build the diffractometer. So the lesson here, it keeps your crystals in the center of the beam, provided that you did a good job centering your crystal properly. So now because you're driving a Ferrari in terms of X-ray diffractometer, you better be careful as to how you push on the gas pedal and what you do when you turn the wheel. Okay, so you need first to center your crystal very, very nicely, because it's going to be important. Any little shift in your crystal centering, we're going to see that in the data all the time. All right, so the data collection speed here is 10 degrees per second. So 10 degrees per second. That means that you can collect 180 degrees in 18 seconds. That's why I made the comment before that some of our users tell us they don't have a life anymore, or they never tell their students or the other professors in the institute how fast the system is. Otherwise, I mean, literally, you know, scientists are getting excited as soon as they see a nice a nice instrument, and so the staff crystallographer is the one in control, and it doesn't always tell how good the system is. 180 degrees in 18 seconds, right? I mean, start data collection, you sneeze, and you go look again, that's it, done. Unbelievable, right? Of course, it's not always like that, but for good crystals, it's gonna go that fast. So when yesterday, when Professor Elena said that they collected about 200 structures in 3 months now, I'm not impressed. No. Yeah, right. So it amounted to about 2 structures a day, I think. Yeah, right? I wouldn't be surprised, not that they've been fully trained and they themselves are getting faster and faster in operating the system. I wouldn't be surprised if, on average, they go up to 4 or 5 structures a day instead of 2. Okay, so provided that you guys keep synthesizing crystals. Right. So now the onus is on you. Okay. Everything is motorized. So the detector, like I said, the detector is moving to the side, okay? But there's also the detector distance that can be changed, and this is all motorized and computer controlled. So why does the detector distance change? Well, this is to be able to collect data on all kinds of unit cell dimensions. So for small molecule, we bring the detector to about 30 millimeters, which is the detector coming right behind the beam stop. And the few days I spent in Professor Elena's lab, every time that I was having the detector coming close to start a data collection, Javier had a heart attack almost every time. Like it's really it takes a bit of time to get used to it. When we have people coming to Rigaku for a demo, right? This is part of my job also, running demos for people. The first time they see the goniometer, all the axes of the goniometer move and the detector move close, they're not used to that, and they're afraid of collisions. Okay. Now, you've got to believe me on that. I am not aware of any collision at all that has happened on our Synergy system anywhere in the world. I am not aware of it. Okay. If there has been 1 or 2 that maybe I haven't heard about, obviously if there were many of them, everybody would be up in arms in the company to fix that. But I've not heard of any collision happening on our systems. All right. So again, the detector comes close to the sample when you have small unit cells like most of your chemical molecules. But then protein people can collect data on that system also. And protein people have crazy unit cell parameters, and sometimes you have to back up the detector all the way to 200 millimeters also. Okay? And so that system is that flexible. So this is the goniometer. So the goniometer, the mechanics of the goniometer, no problem. But the goniometer is nothing if you don't have a proper strategy program. So an algorithm that knows of all the flexibility of your goniometer and can exploit it fully. Okay. So our strategy program is super fast, flexible, and accurate. So the calculation, anytime you change a parameter, the calculations take a few seconds. You don't have to wait for a few minutes for all the calculations to be done for a different detector distance, for instance, different this, different that. It happens in seconds, okay? And again, what is important for you is that the combination of the strategy with the goniometer will ensure that you get a complete data set in all space groups, including the P1 space groups. This is absolutely critical, right? Otherwise, you can't publish. Even if you have a beautiful structure, if it doesn't have a certain completeness to a certain resolution, you are not allowed to publish. Okay. All right, so now this is might sound obvious to you. Well, of course, they have a strategy program. Hopefully, it yields a complete data set. But I'm telling you, it's not obvious, right, to attain all the time. But it does. There are other features of our strategy programs that I don't even think I had the time to mention during my training here in Sao Carlos, but to make the strategy even fancier. The first thing is that it minimizes the time when the phi axis is kind of aligned with the cryo stream. So usually there's a cryo stream or stream of very cold air that is blown onto the crystal, 100 kelvins, okay? And so with the goniometer moving around, at some point, well, your phi axis, that thing here, the axis that goes through the goniometer head will be aligned with the cryo stream, or aligned enough so that now, so you have icing that takes place, but also the mount on which the crystal is mounted, the mount gets so cold that it starts contracting. And now your crystal is going to move down by 50 or 100 microns. It's out of the beam, or it's out of the most intense part of the beam. Okay? So in terms of the strategy algorithm, we have to think about that, so that to make sure that that kind of orientation where the goniometer head is aligned with the cryo stream, I mean, there's not too much time spent in that orientation. Yeah? Okay, that was one thing. So minimizes contraction of the mount to keep the crystal in the beam. Another thing that we have implemented is a so-called cone of avoidance. Okay, because there's something else that can happen when you collect data. This is so it is the mount, again, the middle part of the mount that may enter the beam slightly, okay? And so let me go a bit further. So that whenever that happens, of course, it will create a crazy X-ray scattering background on your images, and that's what I meant, okay? That's that thing happening where the little edge here of the mount enters the beam, okay? And that happens, obviously, whenever you have the mount going too high, meaning kappa going too high, and at the time it's about to rotate during data collection and pass underneath the beam, you may have the little edge here of your mount slightly entering the beam, okay? Like I told the guys I trained here this week, remember that nature is not your friend. It is out to get you. You solve a problem, another problem arises, okay? So we try to solve as many as possible. And so we have to take that danger, potential danger, into account. And this happens whenever you have a loop that is too short, so that the crystal here is mounted so close to the tip here of the mount that as soon as that mount goes up a little bit, then it's gonna enter the beam. And the same goes if you have a bent loop or bent mount, like this one here, okay? So this is another thing that you have to be careful about. It's got nothing to do with the new system. It's true for all X-ray systems. Make sure that you use a good quality loop that is long enough and as straight up as possible. Yeah? All right, so if you don't, and that metallic mount enters the beam, you got something like that, beautiful images, and then an X-ray or a scattering background appears and increases, and then so it overwhelms all your data. There are 10, 15, or 20 images of your data set that you need to reject, and then your completeness goes down to 95%. You have to recollect your entire data set. Okay? So to avoid that, again, and of course that yields very, very bad, I mean, some images with bad data, as you can see here on that little plot there. Okay? All right, and to avoid that, so we implement that cone of avoidance, whereby these are settings. You didn't see me do that, but I set it up on your computer. So we implement a certain width here for the mount, and then we implement also a certain height or distance, really, between the tip of the mount and where the crystal sits. And with that, the program actually comes up with a certain cone of avoidance. And the strategy, all the scans and the images that are supposed to be collected, or rather the strategy will avoid goniometer orientations that will bring that cone of avoidance into the beam. Okay. So all that is working behind the scenes for a strategy program. And again, these are things that you guys don't see, but you need to make sure that it does that kind of work for you. There are always gaps and shadows on detectors also. The shadows, so the gaps come from the different modules that are built together to make a detector. So a detector is never one block. It's always a few chips put together like a mosaic. Okay. So you need to tell the strategy program about that gap. Same goes for the shadows coming from the beam stop and even the shadow coming from the cryo nozzle. Okay, so that as long as the strategy program knows where there's gaps or shadows on your image, it will know exactly where some reflections might be missed. And from the moment it knows that, then no problem. It will recollect those missed reflections on other images a bit later. Okay, so that you get the complete data set. Remember, complete data set. You need to have a good enough goniometer and a good enough strategy program going with it to always get 100% completeness. It's absolutely critical. That's why when I trained you guys this week, when I was showing you how to reject bad data, do that and check your completeness first. And so in terms of gaps and shadows, well, you have two good examples here. So this is the kind of gap that we have on our detector. Of course, the images here are their size has been increased, so the gap is not as large on the detector. And you have a shadow here for the beam stop and a shadow here for the cryo nozzle that happens only for copper whenever the detector has to go far to the side of the beam anyway. But when it happens, it happens. And so we design masks basically to take care or to tell the program where the shadows are, and these are the masks. So these blue things tell the Crystallis Pro you won't be able to collect reflections there, or you will miss reflections there, collect those reflections somewhere else, or in a different crystal orientation. So all that has to be thought about, okay? All right, so I made a little list here of the applications and type of laboratories that usually get the Synergy S. Okay? So type of samples, wide variety of samples possible because there are two wavelengths, copper and molybdenum. So as explained before, very strong and small copper beam first of all. So it's applicable to very small organic crystals as well as coordination crystals, down to 20 to coordination compound crystals, down to 10 to 20 microns. Okay, and that's why I told you that this is here that the limits that you will find come from you, not from the system. It's really suitable for metal organic frameworks, so MOFs and COFs as well, and these two things because the copper beam is small and strong, okay? And so for protein crystals, that system can certainly screen most protein crystals and can collect some data sets that will even allow you to solve the structure of certain proteins. The protein crystals have to become fairly weak for you to not be able to collect a data set, okay? So that was for the copper beam up here. The moly beam now, so up until now, people were rather using moly versus copper because the beams were large and weak, okay? Now that you have beams that are much smaller and strong, you can use smaller crystals. So you can use copper on many more crystals than before, including on a coordination compound, many organic crystals. Okay? You will still switch to moly whenever you have very absorbing crystals. So organometallics with many heavy atoms, and of course inorganics and minerals and stuff like that. But whereas before you were mostly using moly and sometimes using copper, now this is the other way around. You will mostly use copper, and sometimes you use molybdenum. Okay? And so moly here allows you to do high-pressure crystallography. So this is everything that really you can do on the Synergy S. Type of laboratories that buy this system, so labs that need data collection to go fast and that need to be very versatile in terms of the experiments that they want to run. So this is labs with high throughput, so labs with lots of users, and oftentimes, the system is shared among several groups, like here. Universities also with a wide variety of samples, so certain groups working with organics, others with organometallics, inorganics, MOFs, and so on. So large variety of sample. And lastly, so universities acting as facility centers, exactly like Professor Elena's lab. So there's a reason why Professor Elena bought that system, because it needs lots of structures, because there are lots of you using the system or sending crystals for those who are listening to us online. And of course, it's also suitable for a small molecule and protein, so which adds to the domain from the system. Okay, now, come on. The last part before we break for lunch, a couple of things about more advanced crystallography, variable temperature, and high pressure. Okay? Since I'm stopping the regular crystallography part, is there any questions, any comments at all? Yeah, online you don't have anything, no? Okay, all right. Just wanted to make a little stop in case of someone had a question about regular crystallography. So now a few slides only on both variable temperature and high pressure. So variable temperature, of course, this is collecting data at several temperature set points. And you can do that because Crystallis Pro is connected to the cryo system. Okay, so you can certainly run the cryo system independently and set your temperature to a certain set point, and then you collect your data. You can have Crystallis Pro do that for you. So doing that is useful for saving liquid nitrogen. You can ask Crystallis Pro, turn off the cryo system automatically whenever data collection is finished. You're not going to come back here at 2 in the morning just to switch off the cryo system. Okay, so then you ask Crystallis Pro to do that for you. But also, of course, it allows you to tell Crystallis Pro, okay, collect data sets at different temperature set points. In between the data set, Crystallis Pro will then automatically change the temperature. And once the new temperature set point has been reached, then it's going to collect the second data set, and so on and so forth. Okay? So the procedure is really to screen the crystal and come up with a strategy as usual, and then enter a series of temperature set points, and the strategy that you just collected previously, then you link that strategy to each one of the temperature set points that you want to collect data at. So what can be done exactly? So you can cool down the crystal, you can warm it up, you can go both ways basically, or back and forth within the same set of experiments. You can the intervals between two temperature set points has got nothing to do with Crystallis Pro. That depends on the cryo system itself. So those cryo systems, I don't know what their minimum interval is, but let's say it's ½ degree, for instance, then you can set up a series of experiments every ½ degree. Especially when you don't know exactly at what point your phase transition takes place, for instance, you go ½ degree at a time, and then you're going to pick it up at some point. All right, so many temperature set points can be used. Actually, I've never reached the maximum. So that means that, 50 or more probably can be used, right? So nothing to worry about in terms of the number of experiments that you want to run. Importantly, you can also implement a waiting time. So you tell Crystallis Pro, warm up from 100 to 150, for instance, but once it reaches 150, you wait there for so many minutes to make sure that the temperature is stable at the time you start your data collection, which is obviously very, very important. Data collected at different temperatures now are stored in separate directories, so it's easy for you to realize which data set corresponds to which temperature. They are all separated in different directories, and each data collection has been handled just like they are for regular crystallography, meaning that during a data collection, the data is processed and the structure solved automatically for each temperature set point. So that's all you can do in terms of variable temperature. So it's really almost like a regular crystallography. It's just that you have implemented a series of temperature set points, and you ask Crystallis Pro, do that for me over the weekend while I'm going to have fun. All right. So that was variable temperature. I'm going to go over that the interface there, but it's no problem. And then I'm going to spend maybe 10 minutes on high pressure because that's pretty cool. So high pressure means that you put your tiny crystal in the center here of a high pressure cell. It's also called a diamond anvil cell. So when you hear people talk about DAC, it's a diamond anvil cell, and this is something that is maybe sometimes big like my hand here, like my fist, and inside you can put a little crystal. And then you squeeze onto that crystal to build and build and build the pressure on the crystal. and then you collect data at a certain pressure. So Professor Elena has gotten the tools to do that also now, okay? So you see here that the beam goes through here, diffraction happens from the crystal there, and then the diffracted beams come out of the cell from the window here at the back. But of course, you have a little opening here at the front only and a little opening at the back. Okay, so now you're restricted in terms of rotation, how much you can rotate the crystal in the beam, and therefore you're restricted in terms of completeness, data completeness that you get from it. Okay. So here is an example that was taken in Houston. So here is a cell there. It's mounted directly onto the same goniometer head as you use otherwise. So as explained here, it's inserted into a regular goniometer head where the magnet usually is. Okay? Then what you need, because this thing is obviously more bulky than whenever you have a small loop, then you need to create space at sample position. Therefore, the collimator here needs to be a bit shorter. The collimator, the beam stop needs to be pushed away a little bit. So this is actually a different beam stop that is used for high pressure. And lastly, the cryonozzle here needs to be lifted up. Just all these three things just to create enough space here for the cell to be mounted and for the cell to rotate around. All right, so that's how it's done. So the details of a high pressure cell is as follows. So first, you have what is called a gasket. So this is a little thin layer of metal with a tiny hole in there. And this is in that hole that you have everything, the crystal, the pressure medium, and a reference crystal that you will use to actually measure the pressure. But everything is in that little hole. Then on each side of that little hole, you put diamond. And you put the pointy parts of the diamond towards the crystal. And this is by pushing on this diamond that you will create a higher and higher and higher pressure within the gasket. These are diamonds. So synthetic diamond, of course, I think. But these are diamond because they are so strong, but also X-ray and visible light transparent. Because you still need to see your crystal in there to center the crystal. So you will look through the diamonds. But the diamonds are the things used to be squeezed onto the crystal so that your crystal sees higher and higher and higher pressure. And then, so those diamonds they are backed up by this backing disc, right? Then you have the plate here for that make up the outer edge of the cell. You have alignment screws because all that needs to be aligned. You want your diamond to be as aligned as possible. You don't want them crooked this way. And lastly, you have the tightening screws, and so this is by tightening these screws more and more and more that you increase the pressure inside the gasket onto the crystal. All right. Now, experimental setup. So short collimator, longer beam stop, cryonozzle. We saw that already. In terms of the program, it's super easy. On the Professor Elena's computer, every time you open the program, you're being asked, well, what kind of crystallography do you want? Standard crystallography or high pressure crystallography? So you click one box or the other. When you choose a high pressure mode, then probably the most important thing is that Chrysalis Pro now is going to use a much stricter collision model because now you have something bulky mounted at sample position, and that thing, when it rotates, needs space, so you don't want the detector, for instance, to come as close as it would with a crystal mounted on a loop. So collision model is very, very important. Then what you will do also is enter the opening angle of the deck. And I mentioned it already before. The opening angle is that one here and the same at the back. So once you tell Chrysalis Pro that how much of an opening you've got here, the program will know how much or when it has to stop rotating the cell in the beam. You see here the beam, the incoming beam. Sorry, it doesn't work when I want it to work, and it does work when I don't want it to do anything. So what I meant to say here is that you see the incoming beam here is now right on the one of the edges of the opening cone there. So imagine that in this case that the cell would rotate a little bit more counterclockwise, then the beam here will no longer go through the opening cone, and then you've got no diffraction at all anymore. Okay, so and the program will know to the system will know to stop there according to the so-called opening angle that you enter into the program yourself. Okay. So as an end user, for you it's easy to use, but there are a whole lots of things going on behind the scenes in the program to avoid any kind of collision and to collect good data. Okay? So you will also select a shorter wavelength. That's when you go from copper to moly. You cannot use copper to do high pressure, again, because of this short or smaller opening. Okay, let me explain that a little bit more. So here is what you would imagine that you're getting these 3 reflections with copper radiation. Okay, these 3 reflections only are coming out of the high pressure cell. Let's imagine that now you switch from copper to molybdenum radiation. So then the main difference is, of course, that you change the wavelength, and so moly is much shorter than copper. If you change the wavelength, according to the Bragg law, if you decrease lambda here, then you decrease sinus theta, which means that you decrease theta itself, theta being the angle of diffraction. Theta is this. Right? So just getting back to the basics of the diffraction here. So now you decrease that angle of diffraction, you decrease theta. So as a result, what happens? If you look at these reflections 2, 3, 4, this is what happens. 2, 3, 4 now appear here. So because the angle of diffraction is smaller, because of the smaller incident radiation, it's like the diffraction pattern is squeezed together. Okay? So now that not only here 2, 3, and 4 are closer to each other, but now, But now you have also reflection 1 and 5 that can come out of the cell. So where you had 3 reflections coming out of the cell with copper, now you've got 5. And therefore, higher completeness, as shown there on the right-hand side here of the screen. Okay? So that's why you want to switch to a shorter wavelength like molybdenum, because you get a higher completeness. Still, data will be incomplete. There are no 2 ways about it. And this is for that reason now. So see, if I make that cell rotate, here I'm using the entire area of the detector. If I rotate clockwise, then the reflection on the left-hand side is cut out and more. And then lastly, here I've got nothing anymore, because on that last orientation, the beam is no longer even reaching the crystal at all. Okay, so here is another practical example where I'm going to have on the left-hand side, I'm going to have the cell rotate clockwise, and you'll see the influence it has on the actual diffraction pattern here on the right-hand side. Okay, so let's rotate the cell clockwise. So now I've got this reflection coming out of the cell, and that's why I've got basically more diffraction coming. That can be recorded on the detector. Okay, so I go from here to there, and when I keep rotating, this is what happens. Now I'm collecting almost data almost on the entire area of the detector. But then this is on the left-hand side that data will start getting cut out. So it's like an eclipse almost, right? And then at this point, if you look at the beam here on the left-hand side, so you see it's really close to the edge, to the right edge of the cell. If I rotate the cell a tiny bit more clockwise, then I've got nothing anymore. So that's why I'm very restricted in terms of the rotation I can have the cell go through, and therefore I can't collect all the data I need. So what do you do then to collect still complete data sets, or close enough to be complete data sets? First of all, it depends on your lattice. So the lower the lattice of your unit cell, or the symmetry of your lattice, the less completeness you will have. And therefore, you may have to collect on several crystals of the same compound, and then merge all these different data sets together. So many people do that when they do high pressure. So to collect data on several crystals, you can collect a data set on one crystal at a time. but some people even put probably two or a couple of crystals together in the cell. So then you collect two or more diffraction patterns at the same time. You hope that the program is going to be able to, to handle that, maybe as a twin or something, basically as a multi-diffraction pattern compound. And some of our customers have done that successfully with Chrysalis Pro. Okay. So, that's why I said earlier that when you are at the level of mastering high-pressure crystallography, you're becoming a pretty good crystallographer and a pretty good experimentalist also at controlling all these things. Okay. I'm going to finish by one example that I did in Houston. So here, so this is the gasket here with the little hole in it. The crystal is actually that, what is it, like orange or so needle. That other crystal is a crystal of ruby, and this is the reference crystal that is used to check the pressure inside your cell. So basically, that ruby, its fluorescence will change at different temperature, different pressure. And then you need an optical system to measure the fluorescence from the ruby crystal, and the results from your optical system will tell you, will give you an estimate of the pressure inside your cell. And then all around here, you actually have a pressure medium. It's not empty. It's a pressure medium. It's a liquid, so that those crystals, I mean, pressure is applied to all three sides of the crystals, not only on the two sides where the diamond are pointing to the crystal, but also all around. Yeah? So the pressure is equalized on all faces of the crystal. All right, so this is the setup that I had that I used for that data collection. So as I said, the gasket, the hydrostatic liquid medium, ruby pressure reference crystal, and then the crystal to analyze there that needle. And so here, this is the data set I collected. So that one was collected in 14 hours, one crystal. Here is the kind of diffraction patterns I was getting. So nice diffraction reflections from the crystal, but also lots of pollution. So you see these strong reflections here come from the diamond. So you have a lot of things around your crystal. When you do high pressure, you have the ruby, you have the diamond, you have the pressure media, the liquid that is inside the gasket. So the diamond and the ruby will diffract, and the liquid, the pressure liquid inside the gasket will create a high background on your images. Okay, so your high pressure data are usually more, I mean, not as good don't usually have as good a quality as when you do regular crystallography. Okay? So I collected in about 15 hours the number of images and runs, 2 minutes per half a degree. A detector was at 60 millimeters, and here. So I used actually not, in this case, I didn't even use moly, I used silver radiation. Silver is another 0.15 angstrom shorter than moly, so I could squeeze a little more out of the crystal, out of the X-ray reflections coming out of the cell. And so with that data set, so structure actually solved, no problem. It was a low symmetry lattice, primitive monoclinic. So now you see, on one crystal, I could only get 33% completeness because it's monoclinic. And so really there to have a more complete data set, I would have had to collect on 2 or maybe even more crystals. Okay. But that was good enough to actually solve the structure. The R in here, R merge was 5.7%. Final R factor is here below 4%. So no problem solving that structure. So collecting the data and solving the structure was a walk in the park, really. It was harder to set up everything. So that was only the setup of the cell on the system and the data collection, and that's what I showed the guys here in Sao Carlos. But what comes before, and which is on you really, is even harder. This is the preparation of the crystal inside the high pressure cell. Okay, you have to put everything nicely. You have to align your diamond. Remember that you don't want your diamond to slip like that. And you want to put the proper pressure, and you want to mount your crystal actually close enough as much as possible in the center of the gasket. So here, that crystal was probably mounted a little bit too much to the right-hand side of the gasket. The closer it is to one side of the gasket, the more restricted you're going to be when you rotate the whole setup, because let's say that your beam is centered here on the crystal, but that edge of the gasket will pretty quickly come into the beam, and then you have all kinds of crap on your images, and you have to stop the rotation, and your completeness goes down even more. So center the crystal in the middle of the gasket. Align the diamonds properly. It takes. I've never done it. I have no idea how it's done. I've never done it myself. But so this is where typically people like Javier who start high pressure. Oh, you do high pressure? Okay. So typically people who start doing high pressure, they get in touch with someone they know who does high pressure and helps them get going, especially for sample preparation. But this is super cool, because now you can look at the behavior of your crystal at different pressures, phase transitions, back and forth. It's super cool, okay? But it's harder. But this is one more thing that you guys will be able to do now on the new system installed in Javier's lab. Okay? And I think I'm done for the morning.
Any question? Here? So here the guy that is specialty is Guilherme over here. That is from the sync control line. So if anyone have question about how to mount the part that he didn't speak about, he is the guy that you have to work with. Our idea is to form human resources in that area that we will be able to work a lot here. Here, our lab are mainly in the synchrotron, so that will be a very cool area. We hopefully will grow in the next years there. But you said that there was a question from the...
Dr. Pierre, we have a question about the first part. Before you started talking about the temperature variation.
Okay.
Dr. Juan Tenorio from Federal University of Rio de Janeiro asked, what about the possibility to collect high-resolution data for charge density data?
Sure, yep, absolutely, very good question. First, you will switch to MOLE radiation. So this is another thing that, I've actually forgot to mention that in my presentation. But thanks to the MOLE source on that system, the shorter wavelength, remember what I showed you for high pressure here, shorter wavelength with compact the diffraction pattern more than copper does, right? So with copper, you need to move the detector all the way to the side here until this edge of the detector really is almost about to hit the collimator, okay? And this is here that you collect 0.8 angstrom resolution for copper. With MOLE, that 0.8 resolution reflection will be less to the side if this is the beam, but will be more like at medium resolution, medium 2 theta position. But here, obviously, you still have reflection coming here, and those reflections here all the way to on the side of the beam will now come out at 0.4 angstrom resolution. I think that for MOLE, in the corners of the detector, I think we're getting 0.36 angstrom resolution. So to answer that person, switch to MOLE, number one. Number two, and then collect the strategy asking for 100% completeness up to 0.4 or 0.45 angstrom resolution, maybe to be on the safe side, and then increase the exposure time so that this very high reflection resolution will still have enough intensity to be recorded. Which gets me back to one thing that I said at the beginning about the detector. Remember that this detector has no electronic noise, therefore no limit on the exposure time. So if you need to expose for like 2 hours for one image, no problem at all. Okay, so and we have collected again. So at Rigaku, we can't be experts in all these advanced types of crystallography, but some of my colleagues in Europe have collected charge density data with the MOLE source, and there was no problem.
Yeah, Okay, if you want, if you can send us a report or something, information about charge density collected in
Yep.
in Synergy, it will be very cool because that's one of the things that we want to do.
Yep. Okay.
Perfect. Another question.
I have a question about the high pressure measurements. As I could understand from the training and from your presentation now, the only method we have to estimate how much pressure we made to the crystal is to measure the ruby
fluorescence.
Which is the reference crystal, right?
Yep.
And what's your suggestion if I, for example, want to measure 3 or 4 different pressures with the same interval, for example? How can I control the variation of pressure to?
It's really trial and error. I mean, you squeeze more, or you release the screws a little, and then use your optical device to see what the ruby fluorescence is. And then if it's not enough, then you turn your screws one way or the other again until you get the proper reading from your optical system. Right? It's really trial and error. Yeah. So you have to trust the optical system that you use to measure the ruby's fluorescence. And that indeed might take a bit of time, indeed, right? But that's it. There's nothing else to it. Right? Okay.
Thanks.
Perfect. So that's the end of the morning section. We will have a lunch break now. We'll be back here at 1:30 to continue with the next part, where Pierre will continue to explain us how to use the Chrysalis Pro, how are the advantages, the different properties that we can get from there, and probably we will have the opportunity to listen to Luciano too, that will be able to speak about all the real new cool things that are coming. Okay? We will get back here in 1:30 then. Okay. Have a nice lunch. See you.